Good morning, everyone. How are you? This is going to be the third and final installment of the series of our introductory lectures that I've been doing for a while. And today is the crowning jewel of these entire lecture series that I've been doing for a while. The whole idea of what I've been trying to do for the last few weeks is that I've been trying to get a student who never had any R experience, doesn't even know where to download R from, and taking those students and gradually teaching them how to download R and then do basic operations in R so that they're more comfortable with typing code using R, finding their way across the R interface. And today is going to be a very dense and loaded lecture. I think it's going to be a long one. I have no idea how many hours this lecture is going to be for, but it's going to be good for you, hopefully, I think. And the topic of today's lecture is how to get data from the internet. Since we are doing computational social science, all of the time we have to have a research question, a good theory or approach from social sciences, and then a data source, hopefully a computational data source, meaning a data source that reflects human, social, or national level digital footprint. Find a way to get that data, import that into R, clean format, and prepare that data for visualization, for analysis, or if you're building a website, display that on website. If you're writing a report, use that in that report. So data cleaning, data preparation, knowing where to get data, and getting the data actually, I think are several of the most important things that a data scientist should be doing good. So today we are going to be talking about APIs and comma-separated values files, APIs and CSVs. And I will first cover some key concepts and key things to know in lecture format, and then I'm going to transition to R, and we are going to use World Development Index data. First, get WDI data as CSV, work on that CSV, visualize it, do a correlation matrix, and then get the same World Development Indicators data using API and show you how different types of getting that data import, work. Uh, the first, and I think first thing we have to discuss is why are we getting data from the internet? And the idea of getting data from the internet is that social sciences in general uh, have been experiencing a lot of new works, new theories, new phenomena on digital traces and online data. What does, for example, your Amazon purchasing behavior say about your socioeconomic status, your purchasing patterns, your cognitive priorities? On more social setting, for example, are there any social differences between people who listen to classical music on Spotify versus people who listen to other forms of music online? Basically, um, there's so much digital human and social footprint online that an entirely new discipline called computational social science, you can call it social data science, we're interested in looking at these online digital footprints of human beings and societies, basically, and knowing where to find the data and how to get that data is, I think, the first step of any computational research. Um, We can get data as files, so comma separated values files. Those of you who took my IR202 very basic data analysis course, you can find lectures from that course online on my YouTube channel, where we use Excel in order to get CSVs, parse CSVs, build visualizations, and correlation analysis from CSVs. So if you have watched those videos, which I highly recommend that you do, we have been working with CSVs for quite a while. There's also JavaScript object notation, JSON files, XML files. There are different file types that host large data sets. We can get those data, or we can use application programming interfaces or APIs to build a live data access bridge to the platform from which you're trying to get data. Uh, Flight control systems, live tanker and ship trackers. If you are mostly interested in working with real-time data, APIs are more conducive, but they require sometimes payment, sometimes registration. But you should be familiar with both types of getting data, both APIs and also file type. I'm going to teach you scraping later on. It's one, difficult. Two, if you're going to use scraping, you should be very well aware of the ethical side of scraping, because scraping sometimes is not allowed, even when there's a gray area for some web services in which they have no terms of reference related to scraping. Even scraping that data can be problematic. So scraping is something I'm leaving for later weeks. For today, we are going to use one API and two a CSV in order to tap into world development indicators and then get data from world development indicators. Um, Basically, you can get APIs and CSVs from open data portals such as DataGov, Eurostat, UN data. You can get data from social media platforms such as Twitter data, Twitter X using API. You can get data from Reddit, get data from YouTube, and work on digital online behavior of social communities or human beings. There are research repositories like Harvard Dataverse and ICPSR, hosted by the University of Michigan, that host curated data sets. You can use scraped web data. Um, Again, you have to be very careful with the legal and ethical components of using scraped web data. We're going to talk about it later on. There are a combination of these sources. Global database of event language and time combines multiple data formats. Armed conflict location event database, ACLED, does that as well. But at the end of the day, we look at those websites, we understand their data access rules. Do they have readily available CSV files for us to download, or are they giving an API access for us to get data both legally and in the format that those websites want us to get data? So what is CSV? CSV is both loved and hated by the data science community. It stands for comma separated values. Remember last week and the week before, when we were typing our first few exercises in R, we were separating values from one another. We were establishing a vector and using C as the vector, descriptor. We would add different values in that vector, and we were separating them by a comma. And then we would combine all of those vectors into a data frame using the code data frame from dplyr under tidyverse, and build a two-dimensional data structure with columns and rows. And in comma separated values, it is essentially the large-scale version of what we did last week. Each line is an observation or row. Each comma separates one variable and one column. Again, if you took my IR 202, my Excel-based classes, you should be very familiar with CSV files. It is the most efficient form of data storage compared to simple Excel files. It is more economical in terms of hard disk space. You can transfer and store large quantities of data using the CSV format. And it's very universal. It is the oldest, perhaps, of file formats used today. It originates in 1970s and 80s, adapted in the labs of IBM, Microsoft, and Unix-based systems. And it has survived up until today, largely because it is the easiest way of importing and exporting data across multiple systems. So you can write the CSV in a Lotus-based system, send it to a Unix system reads the CSV, you can work on it, send it to a Python-based system, and then work on it, and then send it to an Excel-based system, and it always works. It's the easiest to translate data storage format, and that's why it is simple, it is portable, it's universal, it is readable both by you as a human being and machines as well. And I think it's one of the most survivable relics of past ages of computation. And it's still being used by governments, NGOs, researchers. It is backward compatible. You would see multiple funny memes online about Excel. If you just Google and say, funny Excel memes, certain things are hilarious. But one meme that you would basically see is that entire data sets, financial services, some of the computer-based systems that are still in use today survive on comma-separated values file. So it is the most classical and it's the most frequently used file format. But the problem is CSVs, as you would see here, are just separated. Each value is separated from one another by a comma. But these kinds of CSV files you have to clean first. As it stands, CSV files are not ready for analysis. It's not ready for visualization. You have to do what we in Excel call text to columns, which in computer science terms is called parsing. You have to convert a CSV file into a properly parsed format in which every value is no longer separated from one another with a comma, but each value is properly spread across columns, relevant rows. And even though you have to clean and format CSVs first, these are what we call lingua franca, like the language, the universal language of file transfer formats. A neutral format, anyone can open, no special software, no licenses, no formats, it's just plain text. You can work with a CSV file on Excel, on Python, on Stata, on SAS, on SPSS. Even I'm pretty sure 10 years later, we're going to have a new programming language or a future in which Python and our languages are fully merged, creating a new hybrid language. We will probably still be heavily reliant on CSV files. So it's important in my classes that my students know how to find their way around CSVs. Always funny memes when you're kind of like in the beginner phase of doing like data management, data processing, data analysis. Excel is the simplest form. It is tidy, but Excel files are sometimes not backward compatible, meaning if you created an Excel file in a newer Excel and you try to open that Excel file in an older Excel or an older computer, you run into trouble. Excel files are not economical. They're actually very large file sizes, and it is harder to store reliably a very, very large data sets. And then as you grow in your data science career, especially if you are coming from a background of management information systems, you will be using a lot of relational databases, which is more intermediate SQL, NoSQL, those kinds of things. And when you start mastering data science, you start to look for CSVs, and basically you start to work with CSVs, convert them into relational databases. So it's basically CSV is, I would say, the mastery level of file formats. Now, there are other major data formats that you're going to run into during your data science careers or education. JavaScript object notation is one of those, still lightweight, very popular, easy for web apps, harder to read manually, is more conducive for computers to read. Backward compatibility is not always great because JSON file format is progressing and advancing quite rapidly. A more modern JSON file format may not be backward compatible. Extensible markup language, it's verbose, it's very slow to parse, but basically older APIs, older documents contain XML files. XLSX, again, if you took my IR202, we would take CSV, parse it, and save it as XLSX. Human readable tabular data, very familiar interface, very user friendly, but extremely large file sizes if you go beyond a certain limit. We have tab separated values formats, not comma separated by tab, but tab separated. It's text data with commas inside. It is simple, CSV compatible. It's less common, less backward compatible. Parquet, it's a columnar binary format. It's good for big data analytics. It's compressed, it's good for SQLs, but it requires specialized tools. If you don't have it, you may not be able to use Parquet. More, I would say, niche formats like Feather or Arrow, binary data frame format. They're not human readable. So you would need, again, specialized either like Python or R in order to properly use them. We have structured query language exports or SQLs. They're also very good. Relational databases are useful for a lot of applications, but file sizes are usually very large. So be familiar with all of those data formats. At least I would say JSON, XML, Parquet are the ones that you should be more familiar with. SQLs, if you choose a career in that, database management things, it's going to be useful. But essentially, these are some of the file formats that you're going to run into. Now, API or application programming interface, it's not a file, it's a set of structured rules that allows one piece of software, such as your R program, to talk to another server, such as Twitter's servers, or if you're connecting to NASA and get data from that, you connect to NASA servers. Today, we are going to connect to the World Bank servers using our R, using an API, and get data from World Bank servers in real time. It's not a file, it is basically a set of rules that give data access rights. So if you were to, for example, say, you get API to the NATO database, it basically means that are you allowed to connect to the NATO database and extract data from NATO? So you can create a request such as, give me all posts mentioning climate change from January 2024 until today. The API that you're using checks your permissions via a token or key, which is really like a very large passwords, and it retrieves the relevant data. It sends you a response, most often in JSON terms or XML terms, and your code converts that response into a table or data frame or analysis. This guy here is you, the client. You send a request through the API, and through the server, if the API checks out, it gives you data, and the API gives you response, meaning the file that you're looking for. And usually the API key is kind of like a password style thing, like this. Now, how did we end up with APIs? The whole history of APIs goes back to 1960s, 70s. Early APIs were used inside mainframes to connect internal software components. One part of software within the mainframe talking to another software. When in 1990s, when we started to have the first few examples of the internet, we started to get web APIs. So one external application talking to another external application using online databases. So think of APIs as a data bridge. I think that is the best way I think of them. APIs are data bridges, and for you to be able to cross that bridge, you need to have permission to cross that bridge. And that permission is that APIs can be fully open access, no registration required, such as world development indicators that we will be using today. APIs can be free, you don't have to pay money, but registration based, such as like an email, an institutional account. Some data sources are free, but they're only open for certain universities or certain institutional emails. There are paid and registration-based, very valuable APIs, such as Google API, Meta API, Amazon API, checking the price of something, checking the change of price in something else, and basically comparing prices, comparing price increases, things that would allow you to generate revenue and earn income. Those kinds of APIs are usually paid. Then there's also paid and restricted APIs like intelligence and defense related data, like satellite access API, those kinds of things. I've never used any of them. The most that I use in my own research is paid and registration based API. The ones for my own projects, I use Google API, I use Meta API, Twitter API, TikTok API, so on and so forth. But today, almost the entirety of new data repositories are API enabled or API based, especially just like I said earlier, if you are interested in getting real-time data. This could be if you are interested in tracking flights, for example, there's Flight Tracker API. You can get that real time. There are lots of logistics companies like Maersk, DHL that use logistics transportation data as API. You can use those. But usually APIs are, quite fascinating. And this is what an API request looks like. We're not going to go into this much detail today, but usually you would have a host from where you are trying to get the data, and a password or an authorization given specifically to you or your institution or your research lab. So every single time you request access from that place, you kind of show your ID card, you show your password and say, this is my authorization. And then this is a JSON friendly format in which it has parameters, how much data do you want? How frequent do you want that data? What is the maximum amount of data you want? How frequent do you want that data, right? So every single time you access a host, you show your authorization code, You specify the parameters of getting data, and then you get data through that. Today, I am going to show you both the CSV and API-based data access rules through World Bank data, the best place to practice CSV and API calls. I love world development indicators because it is both very good for learning and teaching these things. But I think if you're like very good with World Bank data, that's a career in and of its own, I would say. A good data analyst, a good data scientist who knows how to pull data from World Bank, work with it, and generate insights, forecasts, and policy analysis from it. I think that's a very valuable skill in today's world. So remember, in my Excel-based classes, we would get World Bank data, create these kinds of hierarchy graphs, line graphs like this. Those of you who took those classes, midterms, finals, were all based on these things. GDP growth line graphs, unemployment line graphs, inflation bubble graphs, inflation bar graphs, creating a world map using those values. These are very, I think, essential skills of a data scientist, data analyst in the way that we are doing it. And in World Bank data, you can get poverty and inequality related enormous amounts of indicators, population dynamics, gender, health, climate, energy use, economic growth, labor market productivity, business stocks. World development indicators is amazing, wonderful, and it's a wonderful place to learn these things, I would say. But before, I think, especially for newcomers, um, both R and Python are very precise and specific with regards to symbols and keyword kind of keyboard combinations about those symbols. You should be aware that in our language, we use four main types of brackets or braces. Standard parentheses, mostly for function calls and grouping, such as like mean x. We have square brackets, mostly used for indexing. And this is the Mac shortcut, this is the Windows shortcut. Some symbols are the same, but I'm working in a Turkish university. My students are mostly using Turkish keyboards. Depending on your computer's keyboard layout, these can change. So I think when following today's like coding lecture, it would be a good idea to find these symbols on your keyboard layout, because the Mac shortcut and Windows shortcut that I have here are for English keyboards. In Turkish keyboards, some of them are really here. Some of them are in slightly like either like right next to it or a slightly different place. Curly brackets, they're good for code blocks, especially when you are working with like HTML inspired or JSON inspired, JavaScript inspired code. You would use curly braces and angle brackets, greater than, less than comparisons. So that brackets and braces is the one key kind of like find these on your keyboard before joining the coding session. You have to also find operators and special symbols. The assignment operator in Python, that it's equal sign, but in R, equal sign is used for a different purpose. So assignment operator, smaller than sign, and then a dash. You assign whatever happens on the right-hand side, assigning it to the object in the left-hand side. Right assignment, the exact opposite. So you can basically type a number of values and commands and assign it to an object that lies on the right-hand side. Equality assignment, which is usually used in our context for mathematical equations or formula. Logic equality, double equal sign. It means it's not statistical or mathematical equal. It means that whatever you have has to correspond exactly to that value. It doesn't have to be numerical. It can also be a string value or a logical true-false value. Not equal, comma equals not equal, especially when we are working with removing empty values, not available values. We use this not equal sign. So when you say my variable should not be equal to 5, it can be anything else, you use that not equal sign. Logical not sign. So when you say exclamation mark true, it means that whatever criteria that I have should not be true. It needs to gather everything that is false. Logical and vectorized, logical and single. So basically, you can combine two values that are numerical with just one and sign. Double and sign basically combines two numerical or non-numerical arguments to one another. We have backticks, um, which basically we are going to use those backticks today. It specifies non-standard variable terms. I'm going to explain to you what they are, but this is not single quotation. This is not double quotation. This is an entirely different keyboard um, button. It is called the backtick. Um, we have pipe operators, Magritte are which links code chunks to one another. We have sequence, we have package function access, we have access variable within an object, the dollar sign, the tilde, the formula operator. We have the power operator, power to, 2 to the power of 3. Multiplication is not x, it's the asterisk sign. Division, addition, subtraction, modulus, which is the remainder. If you're dividing something, it gives you the remainder, and integer division. Of course, this, be careful, it's different than this. This is different than the pipe operator. It takes some time getting used to it. I'm just laying out a general value and keyboard combination kind of thingy so that like you at least understand that you have to find these things on your keyboard. Today, I have given me a new challenge in order to purposefully make mistakes and then solve those mistakes together with you. I'm using an entirely new keyboard. I'm really not familiar with this keyboard, so I'm going to search for some of these keyboard signs with you, get frustrated with you, but frustration is not necessary. We'll just find a way to fix those problems. Quotes and apostrophes, single quotes, double quotes, most of the time interchangeable. Backticks, it's a different thing. It's like the angled single quotation sign, right? It's important. Single quotes and double quotes are to refer to a string or an object value. Backticks are for non-standard variable names, a weird name. So especially when we are referring to specific variable names in World Development Indicators database today, we will be using a lot of backticks. Comment, uh, non-executable thing. You basically write yourself comment a text as a reminder. As for object slots, you might use it, you might not use it. Help, variadic arguments, probably you won't be able to use it today. Underscore, native pipe, access non-exported functions, we're not going to use them today. So these are basically the most commonly used keyboards, like symbols that you should find. If you have any trouble, you can just like bring out your keyboards layout options and then have a look at where in your keyboard are these interesting functions. Now, the second thing I want to talk about is that both R and both Python are heavily package dependent. What does that mean? If you want to create a network analysis, if you want to create a map, if you want to create a specific visualization, if you want to create a specific kind of regression analysis or a correlation analysis, if you want to get satellite data, if you want to connect live to the NBA database, I don't know. Anything you want to do in R works for Python as well, is packages. Package ecosystem is a very important thing in data science. And this network graph shows you the connectivity of our packages, the ecosystem of our packages. So you would see that dataplier or dplier is the most like popular in this group. It connects a lot to tidyr. It connects a lot to Tibble, magrittr, data table. So this part is data cleaning, data formatting cluster. ggplot is basically the data visualization cluster. Mapping, map tools, maps, ggteams, ggmap, simple features, SB, raster. This is the mapping part. Shiny cluster, if you're trying to make interactive visualizations and put it on a website, you use the Shiny ecosystem. So basically, depending on what you're trying to do with R, you usually bring a number of packages, install packages, library packages, and then bring in a combination of packages to the R in order to be able to do what you want to do. So R has a very rich, very well maintained community of packages. Most of those are created by other data scientists. Some of them are created by computer scientists, some by statisticians. But sometimes newer students ask, when I say install packages, where are we installing packages from? And the answer is the Comprehensive R Archive Network, or CRAN. When we first downloaded base R, the brain R, not positron or not RStudio or not VS Code, the base R we download from Comprehensive R Archive Network, CRAN, basically we call it CRAN. And every single package that's the most used in the R framework, we also download from CRAN. Now, there are also packages that are newer, created for a different purpose, created for Python initially, but also used in R. We most of the time download them from GitHub. I'm going to show you how to use GitHub in later lectures. It's going to complicate things unnecessarily for now. But we download packages most of the time from the Comprehensive Archive Network. So when you write install packages, tidyverse, it is downloading tidyverse from the Comprehensive R Archive Network. So that's the thing that you should really know. What are some of the core packages for the purpose that we are using? So if you are doing core data science and data wrangling, data cleaning, data manipulation, dataplier, data table, we use them to filter rows, reorder data, create new variables, so on and so forth. We use tidyr for data tidying. It helps you reshape data, convert white tables to long format, and vice versa. We do data import export through readr, readexcel, Haven, or Rio. Basically, we use them to read files like CSVs, Excel, SBS data, or SAS into R. Data cleaning packages, janitor, string R, lubridate, clean messy column names, fix text strings, and handle dates and times. Functional programming, per, lets you apply functions repeatedly like map or map data frame instead of writing long loops. It's good for automating repetitive operations. Tibble Magritte-R creates modern readable data frames. Magritte-R provides the pipe operator that we have been using in class. For data visualization, we most of the time use ggplot2 or a grammar of graphics plot, the gold standard for data visualization in R. Any data visualization that you can think of comes from ggplot2. Interactive plots, Plotly, ggigraph, HighCharter, if you want to create not just a visualization, but an interactive visualization in which you can hover with your mouse, like click on it, like modulates and whatever. We use most of the time these packages. Tmap, leaflet, map making packages of R, plot combinations, co-plot, patchwork, ggthemes. Sometimes people want to create extremely colorful graphs and funky, color combinations. So R, Color Brewer, Viridis, Wes Anderson, the famous producer and director. For GIS specifically, spatial data handling, simple features. Raster data, we use the raster package or the Terra package, especially for elevation models or satellite images, using actual mapping, leaflet, tmap, map view, spatial statistics, SPDEP, spatial regs, meaning spatial regression. Geocoding is ggmap, OSM data, GIS integration with low-level geospatial operations, RGDAL and RGeos. Probably you will be using these along the way in your career journey in data science, but I'm just like scoping out some of the packages. General network analysis, if you're doing something simple and static, iGraph, tidygraph combines iGraph's power with dplyr-like syntax, analyze networks the same way you analyze data frames. For visualization and interactives, gggraph or ggraph or grammar of graphics graph, Viz network or visual network, network D3, a three-dimensional kind of network thing, dynamic networks, social network models. We will be using some of those in our network analysis week. For text mining, we use TM or text mining package, Quantita, tidytext. To do sentiment analysis, we use SuseNet, Sentiment R, text data. For topic modeling, we do topic models, structured topic model, STM. Text to vec, Word to vec, RVest for web scraping, HTTR, JSON Lite. For NLP tagging, SpaCR, UDPipe. You don't know these yet, but at least in your in some kind of your mind, it's important for you to at least know that these packages exist for these kinds of purposes. Machine learning we'll do maybe in the last lecture or the lecture before that. Caret, tidy models, random forest, ranger, XGBoost, LightGBM, CatBoost, Keras, Torch, and Net. So these are all machine learning and statistical packages, or R. You download them and do deep learning, convolutional neural networks, and whatnot. Time series forecasting, forecast FPP3, profit, model time, mostly for like time series predictions of certain things. So if inflation has been declining in the last 10 years, what is the likelihood of inflation declining in the same percentage in a way? Project management packages, dynamic reporting packages, API and data integration packages. It is important, I think, to know that these exist at the end of the day. Now, some of the questions that I get from students is usually very frustrating. Like, these package names, they make absolutely zero sense. Like, what is Magritte-R? What is dplyr? What is ggplot2? Like, it really doesn't make any sense. And I agree. Um, R's package naming is not really user friendly. And R has a long tradition of like whimsical, pun-based, cryptic package names. It's a mix of hacker humor, academic culture, and open source creativity. These are named essentially this way for it to be fun. It's a nerdy fun, but I mean it's there for fun. Early R and S, its predecessor, developers came from statistics department, not like corporate labs like Stata or SPSS or Excel. And so naming these packages was something informal and playful. It was kind of like a rebellion against too serious and too corporate computer language and culture, which is like very strict, very precisely named, almost like militaristic in the way that corporate programming languages were naming their software. So R and S were developed by people who were rebels in that sense. So they use a lot of inside jokes, they use a lot of wordplay. And of course, while they were having fun, you as newcomers to this field get confused. You know, what is dplyr? Like, how would I know what I should use this strange sounding package for? It's data plier. Plier is a tool that you manipulate metal or pliable metals. So you basically use a plier to manipulate data. ggplot2, grammar of graphics, it's a plotting system. Lubricate dates, meaning make it easier and smoother to work with date variables. String R, operations on text, basically strings. So forcats, for categorical variables. And I think in a way, developers enjoy leaving personal or cultural fingerprints instead of naming packages after themselves. They name caret as classification and regression training, simple features, SF. Magritte R, it is named after the surrealist painter René Magritte and the pipe, Ce n'est pas une pipe, if you know the painting, the whole surrealist connotation of that this is not a pipe. So it's a very insidery joke. It's very difficult. It's not very accessible from the outside. And the only way these package names end up making sense is like further along the way. The more you use it, the more you understand why they were named this way. But they're supposed to be fun, expressive, trying to make like statistics, statistical computing, data science less serious, more fun, and more like enjoyable in a way. And also keep in mind that the entire R ecosystem is open source. You're not paying any money for this, guys. Remember, you're not buying it like you're buying Stata. You're not subscribing it like you would Excel or like Microsoft Office. There's no subscription. You're not buying anything. Everything that exists in the R and Python ecosystems are most of the time free. And they're wonderful programming languages, just given to you for free. And so because people who are creating these packages are not employed by R doesn't employ people. It's just the community of open source programmers and coders developing this language. They just name things in any way they want, right? There's no money involved. They don't have to do anything. If you have problem with R, there's no customer service. You can't call a customer service and say, "Oh, I can't do these things." You have to fix it yourself. This is open source. You're not paying any money, which is good because you're working on something that's free. But then the entire responsibility of things going wrong rests entirely on you. And the same thing goes for naming these packages. These packages are named in any way that their programmers want it. So if in the future you become a good data scientist, you become better with R, you start creating your own packages, you can just create a package in a way that you want. It's entirely up to you. Hope it becomes popular. The other thing that we'll be covering today is the data pivot, the wide to long format. So wide format data and long format data are essentially different ways of storing and displaying the same information. The wide format is that each variable has its own column. So, for example, in today's World Development Indicators data, you will have a country variable column, values for 2020, values for 2021, 2022. So it's like horizontally spreading data. It's wide format. Every variable is its own column. It's very common in spreadsheets or survey data. Long format is that each row is one observation for one time or category. So this above data, when it's converted into long format, it becomes country, year, value. It is spread in a longer format. It spreads vertically this time. And this is useful for analysis and plotting and modeling. So wide format is used for data storage and containing large amounts of data in an easily accessible and readable fashion. It's better for tables, it's for summaries, whereas long format is usually more preferred for analysis and visualization. One of the most essential skills of a data scientist, I would say, is to convert a wide format data to long to wide. Essentially, you convert wide to long to wide using pivot longer function of the tidyverse package system or pivot wider. You basically create conditions by which that longer data has to be converted into wide and wide back into long. And you always can check the structure of your data with the glimpse function. It's going to show you whether your data is wide form or long form. So this is basically two ways of representing the exact same data. The one on the right is the wide format, good for like creating a table, getting a glimpse. The long format is mostly good for time series analysis and visualizations. And you're going to understand why in a moment. But before we go into the coding part, we'll be covering quite a lot. I need to explain, even very briefly, what you'll be encountering today. Probably, I mean, this is a 400 coded course. I'm assuming most of you have learned about the Pearson correlation, but in case we have students coming from outside the faculty, maybe you never took a statistics course, a Pearson correlation is named after Carl Pearson, an English mathematician and a biostatistician. So he has been credited with establishing the discipline of mathematical statistics at the University College London in 1911. And there are different types of correlations, but the one we're going to be using today is going to be the Pearson correlation. It measures the strength of the linear relationship between two variables. People who are tall, do they also weigh heavier compared to others? This means that if I have an x-axis and a y-axis, let x-axis be a person's weight and y-axis be that person's height. And if we sample, let's say, 1,000 people from our university, for example, we measure their height, we put them on a scale, measure their weight, and say that person one, weighs 50 kilograms, height 1.67 centimeters. So you have 1,000 data points. If you put them on an x and y axis, you would notice that the taller a person gets, the heavier they end up weighing. There are outliers. There will be tall people who don't weigh that much. There will be shorter people who weigh quite a lot. They're called the outliers. But depending, even with the outliers, you're going to see a general trend in which most of the time, the taller a person is, the heavier they end up weighing. even when taking into account outliers, that people that lie outside this trend line. So if the relationship between height and weight has a big correlation, which we would expect, we would say that the correlation is closer to +1, meaning a total positive correlation. But for example, let's take two completely unrelated variables, like a person's height and how much ice cream that person ate in the last year. Entirely no meaning whatsoever. And if you have again an XY axis in which let Y be height of the people that we are sampling, those 1,000 people from our university, and let the X axis be how many times each person ate an ice cream in the last year. And when you plot that, you're going to see really no correlation. They're completely unrelated phenomena because we can't say tall people eat more ice cream. There's no such thing, right? So +1 means that these two things are correlated quite a lot. 0 means they have no relationship. -1 is that they are inversely correlated. So for example, I would assume that people would eat more ice cream in summer. So I would say that actually, no, that's still a positive correlation. I was going to say the more temperature increases, the more people eat ice cream. You can say, for example, that I would expect those 1,000 sampled people, they would wear less raincoats in summer compared to the winter. So you can say things like, as the temperature increases, people who wear raincoats decreases. So that would be an inverse correlation. When the outside heat increases, tendency to wear raincoat decreases. One increases, the other one decreases. That is an inverse correlation. Then you would plot this somewhere closer to -1. So R in that context, not the R programming language that we are using, but R and R squared values that we use here. It's called the Pearson correlation coefficient, or also known as Pearson's R. It ranges from -1 to +1, where +1 indicates a perfect positive linear correlation, linear relationship. -1 indicates a perfect negative linear relationship, and 0 indicates no linear relationship. So this is basically how they look on a plot. So this you would see is a nearly perfect correlation. This usually happens when you are correlating the same variable with itself. One is usually an unrealistically high correlation. This is 0 correlation. The plots are all over the place, no relationship. And this is inverse correlation. As one thing increases, the other one decreases. These are different plots that show weak correlation, very weak correlation, medium correlation, strong correlation, and very strong correlation. And you can actually go to rpsychologist.com/correlation. It's a very nice interactive website in which you can understand the logic of correlation better in an interactive where you can move plots values around to make it more correlated, less correlated, nonlinear curve, so on and so forth. But essentially, at the end of the day, correlation gives us the tendency of two variables to follow each other value-wise, whether they are increasing together or decreasing together, increasing together very strongly, increasing together not so strongly, how many outliers there are. And at the end of the day, we have an R value in which 0 is very insignificant, -1, super significant but inverse, +1, super significant and direct relationship. And so this, on the other hand, is a correlation plot. correlation matrix, in which multiple variables have this one-to-one comparison between one variable compared to other variable. You're going to see that every variable's correlation with itself is perfect one because it's the same value. But we have some values slightly like really insignificant but minus correlated, inversely correlated. We have a 0.5 moderately correlated. We have quite strong correlations, 0.8, 0.88, 85. This gives us a quick glimpse of comparison between multiple variables where we can see whether one variable is strongly correlated with another variable or not. So today, in World Development Indicators, we're going to create this kind of a correlation plot. But it is important for me that you understand what these values are, like minus 0.2, like 0.1, 0.2. So it basically gives you the correlation between weak and opportunity points. I don't know where this data is coming from, but visually, this is exactly what we are going to be doing today with world development indicators. But each of these values, 0.5, 0.6, 0.2, is basically a correlation output between two variables so that we can judge whether they are related to one another. That relationship can be pure chance. There can also be a causal relationship, but correlation is just correlation. It gives you the tendency. In order to do causal work, you have to do causal measurements, which is an entirely different topic for another week. Even by now, I'm thinking some of you, especially those of you who are taking this course for the first time, taking R for the first time, you are probably starting getting overwhelmed, and I don't want to overwhelm you further. But another thing that I need to explain is that dealing with not available values. What is NA? NA means not available. It's a placeholder for missing data in R, in Python, and Excel. It's not zero, it's not blank, and it's not null. It's definitely not zero. It's like this value exists, but we don't know what it is. And especially in world development indicators data, NA values are, let's say there is a war in a country, or there has been a natural disaster, or some kind of a national crisis. That year, that country's statistical office has been unable to measure inflation properly, or unemployment improperly. Like unemployment exists in that country, inflation also exists in that country, but the institution that does that observation and reports it, which is usually the statistical offices of that nation, for some reason couldn't collect the data, either this, because of a war, because of a national disaster, because of a natural disaster, whatever. They were unable to collect it. So you would see in world development indicators for some years, for some countries, important econometric data appears empty. It doesn't mean that it's zero. It doesn't mean that unemployment in that country was zero. It doesn't mean that inflation in that country was zero. It just means that nobody observed. So the values don't exist and the value is not available. So dealing with NA values, not available values, is another critical component of doing data science. We usually detect missing values in R because remember, in Excel, we were doing find and replace. We were finding missing values in world development indicators and basically converting them into empty, not available values. So that when we're building a visualization, building a graph, we don't get errors, right? The same parameter happens in R as well. So is dot not available X checks which values are missing. Sum is not available X counts how many are missing. Any not available data frame checks if any missing data exists in dataset. So these are basically the code samples that allow us to detect not available values in a dataset, so that you develop a strategy of how to fill or empty those values. So if you say not available omit in data frame, it drops rows with missing values. When you say only complete cases in the data frame, it leaves any other input that has not available values and selects only fully complete rows. And logical or Boolean arguments like not available remove true, or inside functions like mean in X, not available remove is true. It basically removes all not available values. Usually we don't replace missing data, but assuming you're dealing with a different kind of data in which replacing missing data is allowed, you can do manual replacements in which all not available values in the data sets convert them into 0. Or take the mean, a statistical average of other values, and replace that value with the statistical values. But you can't do that in most data sets. It has to be a very specific data sets in which you can allow. Definitely, we can't do this for world development indicators. We just have to drop not available values. Definitely don't delete. Understand why that data is missing. Has there been a survey error? Has there been a dropout? Is that missing value is therefore by design? Has there been a problem with observation? And then decide what kind of not available value dealing mechanism that you'll be using. Now, finally, I really need you to know how to copy a file path. What is a file path? A file path is basically the file trajectory of whichever data that you are using. So we are going to download a CSV file online. It is going to be downloaded into our downloads folder. And in that downloads folder, we are going to copy the path name of the file and import it into R. And I'm going to show to you step by step, but I'm using a Mac. So those of you who are using a PC, you can also do this. In the File Explorer, you right and shift click on the file and click copy as path and then paste into R. The path appears with backlashes. You have to replace all of those to backlashes with forward slashes in PC. In Mac, you right click on the file, you press option, copy file name as path name, and paste directly into R. So if you are trying to import a CSV file into R, you are going to be using read CSV command, quotation marks, the file path, and then you assign that CSV file into an object. But it's important for you to be comfortable mostly with using file paths. You can also bring file into R's own working directory. Working directory is the directory, the folder in which your current R session is. You can get working directory here in order to learn what is the working directory of your R. And if you want to set a specific folder into which you can download files, and without doing this copy file path thing, directly refer as the data CSV, you can just set your working directory to whichever folder that you want to work with. But we don't always work with our own computers. Think you might be in a lab working with 100 other people. You might be working on um, a server or a computer used by 10 other lab members. That happens. So in that case, um, I I would much prefer you to be comfortable with working with a file path rather than setting a working directory, which you may not be allowed to do so in a shared environment. In a shared environment, whoever your lab manager is, whoever your PI is, would be very specific where each folder should be, from which folders they have to be accessed from. So if it's your like own personal projects, you can do set working directory. But if not, the way I teach these things is to using the file path copying and pasting. It's more it's better. Good. So now let's pause here a little bit. I'm going to get some tea. You can just like pause and continue this anytime you want. I'm going to get tea and I'll come back in like 5 minutes. So see you. Okay, let's continue onwards with the coding and data analysis phase of the lecture. The first part was about concepts, things to know, keywords or operations that you may not know of. And now we're going to do an applied study of everything that we learn. The first thing we do, we go to Google and say World Development Indicators. It's going to take us to the World Development Indicators data bank of the World Bank. Um, if you're new to this, I have other lectures from my quantitative data analysis with Excel course, in which I explain this interface in huge detail. Just briefly, this is a data interface that allows you to extract whichever indicators you need from the World Bank. And you basically have a database section, a country section, a series section, and a time section. So in the database, we have world development indicators already selected, so we're not changing that. In the countries, it says all, or countries, or aggregates. Aggregates are country groupings, either socio-economic country groupings or geographical or continental country groupings. We don't want these. We want countries only. So make sure that this tab is selected. This contains 217 sovereign territories in the world. We click on select all, which basically allows us to select every single sovereign territory in the world. We go to series. Now, series contain indicators, variables. And today I'm going to be working with the GDP variable, gross domestic product, and just nominal, simple US dollars yearly GDP value. So as you're going to see, just World Development Indicators data series contains 1,500 data point indicators. We can sort this by typing GDP into the search bar and then clicking on the search, which somewhat reduces to 89. We scroll just a little bit until we see GDP current US dollar. LCU is local currency unit. So for example, if you're looking at Turkish GDP, local currency unit is Turkish lira. So it's going to be in lira terms. If it's like Eurozone, it's going to be euro. So any local currency will be in the LCU. But current US dollar is the latest inflation adjusted US dollar value of every country's GDP. We will be working with this. Don't pick others. GDP current US dollar. And then I'm going to show you how to do a little bit of time series mapping as well. So we need all the time that we need. So this goes back to 1960. Starting with 1960, I'm going to be picking all of the countries. This is select all. This is unselect all. This is invert selection function. So I need select all. So I'm going to select all. I do apply changes. So if everything is okay and fine, in the preview section, I should have each country, for example, like let's look at Estonia, each country's GDP. Now notice, for example, Estonia starts its GDP value report beginning with 1993 because of the USSR and the Cold War. It wasn't Estonia, the Estonia we knew today. So these are missing values. These two dots that you see is World Bank's designation of a not available value. Remember, we discussed what a not available value is. So we have to develop a plan in terms of how we have to deal with those not available values. Let's look at Germany. Germany should have data that goes all the way back to 1960, so no problem. India, let's see how far it goes. It is also very, clear. But for example, in Syrian Arab Republic, you'd notice that the wartime indicators, well, GDP is actually quite good. But this year, because of the revolution, there's a new state, probably 2024, is not available. So any big major problem in that country would usually result in not available values for that country. So what we need to do now is that we have to go download this, not Excel, not tab text, but CSV. We need to import this as CSV because Excel and tabbed format often contains errors and have backward compatibility issues. So CSV is the gold standard of everything. Not everything, but like data storage formats. So I clicked on the CSV. It has downloaded this into my computer. So I'm opening up my downloads folder with everything that I have downloaded, papers that I will hopefully one day read. But as you know, this is a zip file. Zip means that multiple files are zipped, clustered in one single compressed file. In PCs, you need to open this zip file and extract its contents to your desktop or another folder. But in PCs, you really have to extract that zip, unzip it. That's such a wrong thing to say, but the technical term is to unzip. There's nothing I can do. So in PCs, you have to unzip. In Mac, you double click on it, it automatically creates a folder here. Here, we have two files, a metadata file and a data file. I am going to be working with the data file, this one, not this one, this one. So remember, in the lecture part, we discussed how to copy path name. We could also have downloaded this to the working directory of my R session, but I want to show you not the harder version, it's not really hard, but the version that's going to be useful for you in a crowded lab project setting where you're not allowed to set working directories. The PI has a very specific folder system. You're not allowed to disrupt that system. If you disrupt that system, it's going to be very, very bad. So you use with the folder system that you have to use. So in this context, I'm going to right click on this. A menu appears. Now, when you hold the Option key, you're going to notice in Macs, it says copy blah, 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 as path name. This is the data file that I had to work on. So I'm going to hold the Option key on Mac. In PCs. In the first part of this lecture, I explained to you how this is done in PCs. If you are struggling, you can always say, how do I copy file path name on a PC or on an older Mac on Google. So I'm copying the path name of this. Again, I came here, I pressed Option, it says copy the data CSVs path name. I clicked on this. Now, all of you open a new fresh R session, clean environment. If you need to clean, you can use the broomstick option here. There's a broomstick here. There's a broomstick here. There's a broomstick here. If you need, you can just like close the R session, create a fresh new R script from scratch. So once you have your fresh R session, first thing I'm going to be doing is that I'm pasting the path name that I just copied. It's in the memory of the computer. So when I press this, it says users, my name, downloads, p data extract from I mean, a lot of verbose, folder, subfolder, 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 the actual data that I need to work with. Now, don't forget that there is a quotation sign here and a quotation sign here. This is single quotation here. You can use double quotations as well if you want. Now, I am adding an end parenthesis here, and it is going to give me an error because it says, where is the beginning of this parenthesis? And I have to also add an opening parenthesis here as well. Once it's friend, the opening parenthesis is here, the closing parenthesis is here, you no longer have any trouble or an error message. Now, what I'm going to do right now is that I am going to use the read underscore CSV command, and I'm going to read the contents of the CSV file. Sorry, I did this completely wrong. Read underscore CSV basically reads the content of this, and I will be assigning the contents of the file, the CSV file that I downloaded using the read CSV function. And let's create a name for this. Let's call it data. You can say that World Bank data, World Development Indicator data. To make it simple, right now I'm going to be doing data. Now, first thing is that when I run this, it says error in read CSV. There is no function called read CSV because there is a function called read.csv. There is no function called read underscore CSV. These are two different CSV readers that have different protocols in importing CSV files. The read.csv, the one you see, is in the utilities, in the base R, the R that we downloaded. The read underscore read CSV belongs to our good friend dplyr, which is in the tidyverse. Now, if this is your entire first time doing these things, you might need to do install packages and do tidyverse. It's already installed in my computer. If it's not installed in your computer, do install packages tidyverse. If it's installed in your computer, just click on library tidyverse, and it takes tidyverse, the entire package ecosystem that contains data manipulation, data visualization, data formatting, all of the useful stuff, in almost the entirety of Excel's key functions imported into R. Now that I have installed tidyverse, which contains dataplier, forcats, ggplot, lubridate, per, tidyr, tibble, stringr, readr, it is now going to understand this read CSV command because this read underscore CSV belongs to tidyverse. Read.csv belongs to base R, right? If it's complicated, yes, it is, but it's going to get better as we move further. So now I'm running this command, data read CSV, and it is, our data is not that big. It has now a data object which contains 2022 observations, 69 variables. Let's click on this data and see what's happening. So this, I mean, for those of you who have never worked with world development indicators, this is what world development indicators data looks like. So you have country name, all 217, no, yeah, 217 sovereign territories. Their country code, ISO 3 country codes, because sometimes different countries have different legal names across different data sets. So for example, in one data set, it can be Syria. In another one, it can be Syrian Arab Republic. There are, for example, other countries like Venezuela. In some data sets, you have Venezuela. In some other ones, Venezuela, RB meaning Bolivarian Republic, Republic Bolivarian. So RB Venezuela, it's the formal name of the country. Same goes for Iran, for example. Is in some data sets, it is just Iran. In others, it is Iran Islamic Republic of the formal name. So because these country names can be funky across data sets, in order to create one singular code structure that refers to that country, in all data sets, we have country codes, which is ISO 3 codes. Iraq, even if its name changes tomorrow, its ISO 3 code is going to stay the same, IRQ. Turkey, is it TUR, I think? Yes, Turkey, TUR. Remember, Turkey used to be Turkey, now it's Turkey. We changed our official name. India wants to change its official name to Bharat as well. So even if that country's official name changes in diplomatic databases, its country code stays the same. That's why we have country codes. And then we have series name. So we downloaded GDP current US dollar and a series code. Now pay attention to this series code because when in the next exercise we're going to be using the API, we'll be downloading data using the World Development Indicator API, not a CSV file. We will be calling this data, GDP current US dollars, with this specific series code. So these series codes are World Bank's native codes. Let's see if in the series code. So notice here we clicked on GDP current US dollars. If you click on the I button, information button, it is going to give you the series code right next to it as well. This series code is the series code that we'll be using when we are calling, because API requires specific non-mistakable codes. You can't do a successful API call with this. You'll be able to use this as your API call. So for now, this is not important. In the next exercise, it's going to be important. Now, my years are starting from 1960 and then year 1960. So I have two designations of years. It starts from 60, goes 2005. In R, there's a limit. So these are these, data frame browsing buttons here. So it shows 1 to 50 columns. Here, when you click on this, it continues from 1960 and goes all the way to today. If you want to make sure to reach the latest part, you click on this like double next or double previous sign. Double previous takes you to the beginning of a large column array. End takes you to the end. Sometimes you have data sets with columns, like hundreds and hundreds of columns, be like larger data sets. And that's why these are important in that context. So um, one problem though that I have is these are two dots, empty values. So in Afghanistan in 1960, there was no GDP data. 61, 62, we have a lot of not available values in this data. In Afghanistan, GDP data starts flowing in after 2000, after the US military intervention. Albania, same thing. American Samoa, same thing. There are lots of countries with missing values, and it makes large country, large time comparisons difficult. So you have to pick your battles. You either limit your analysis to a smaller group of countries who have data since 1960, or if you want to compare all of the countries, you have to compare. Uh, what's this country that never has a data? Oh, North Korea, Democratic People's Republic. North Korea. What is this? Kosovo. It's we still do not have okay, so what we're going to do right now is that I have to specify these two dots so that R understands that these are not available values. So sometimes not available values, okay, we have some newcomers, so I have to go slow. Data, read CSV, the pathway of the file, and the parenthesis ends here. Now, what I'm doing is I'm going to the left of the parenthesis. My cursor is blinking in the left of the parenthesis and right at the quotation mark of this CSV patterning. I add a comma. Sorry, that's not a comma. This is a comma. I add a comma and I hit enter. When I hit enter, notice that it is starting indented. So it is basically pushing, it's not bringing the parentheses all the way to the left justified. It basically, because I have a comma here, it means that I'm going to continue this code. It's like when you're writing, adding a comma means the sentence is continuing, right? So after the comma, before the end parenthesis, I hit enter and it indents my parentheses so that the paragraph flows, so that it still connects to this read CSV code. Here, I'm going to designate the not available value as a vector. Remember, we learned how to do vectors in last week and the week before. It basically starts with C, cell, a cell of arrays. So I'm going to add here some values that normally connotate not available values in many data sets. So the first way of a not available value is emptiness. What I've done here is that I added a quotation mark, which automatically brought its own closing quotation mark because RStudio is helpful like that. I'm only clicking on one single quotation mark and it immediately closes itself. Now, this is one type of not available value, just like nothingness, no value, nothing. Two quotation marks have nothing in between in this context. Comma, the second way not available values manifest themselves is by explicitly calling themselves not available values. So if you wanted to remove not available values, detect not available values, you would either find nothingness. It's such a meta thing to say, a phenomenological coding, right? Instead of vibe coding, we do philosophical coding here. Where we're high quality like that. So either you have nothingness or an NA value. And in our case, the data not available values are these two dots, which connotate not available values. So with a comma, I also open parentheses dot dot. These two dots in my data set connotate not available values. So that is basically how I explain to R that in my data set, if you find an empty space, if you find an NA, or if you find two dots, treat that as a not available value. It might sound nerdy or just too laborious. Data cleaning is the most important part of any data analysis or data science thing. So now I have this command tied to the command above with a comma here. And then I'm going to run my read CSV command again and then assign them to data. And now I go back and check. Now notice all of these two dots have been converted to null values, not available values. Now R understands that, oh, so these two dots are not available values. So I'm going to change those two dots to not available values, empty values, in a way that I understand. Wonderful. Now, let me add, this is a new keyboard. I explained to you, this is the first day I'm using this keyboard. Talk about a challenge. I have no idea where any of the symbols are in this, because I mean, I want also, I want you to see me struggling as well, because sometimes when newcomer students, it's new for them. They don't understand anything. Everything is overwhelming. And then when, the lecture is like perfect with everything, like it's a little bit intimidating. So my way of teaching is that I struggle a little bit myself as well, try to find the solution to my struggle so that like you make peace with making a mistake or just like not knowing. Because most of the time, when we write something, we either look at a previous codes, go to Stack Overflow, go to GitHub, sometimes ask a GPT, but GPTs are still not very good in writing, especially our codes. They make a lot of mistakes, so you need to have a human eye catching those mistakes as well. So don't feel like a good data scientist just writes those codes quickly. So I like to struggle. So remember, we have this hashtag sign, which hashtag means commenting, which means, where's my equal? Um, non-executable string, meaning text. Anything you write after a comment is not executed. So for example, let's say some sentence. No, just some sentence. I'm running this. It says unexpected symbol in some sentence. I have no idea what you are trying to say to me. And then if you use a hashtag in between, it says run. I said, oh, so this is a comment. I'm not running this. It's just like some nonsense that you wrote that you only understand. We use hashtags to leave messages to ourselves, our lab colleagues, our PI, reminders to ourselves, right? So we just use hashtags as a way of taking notes, if you will, on the code. And here you can basically do, for example, three quotations and say, explore the general structure of a data frame. So here we have two commands, glimpse, get a glimpse of your data. It's like the transpose version of print. Columns run down the page, data runs across. If you have a very large data set, glimpse allows you to just get a quick look at your data to remind yourself what this data is about. how it's spread, whether it is wide format, long format, what are the variable names, what are they like Boolean operators, string, numerical. So we say glimpse. What are we glimpsing at? We are glimpsing at this data, the CSV in red version and incorporated into I mean, probably naming this object data wasn't a good idea, but still, I'm going to pursue my mistakes. It's basically this data. I'm glimpsing at this here. Glimpse data. This is this data that I have. The world development indicators data. Of course, these commands like glimpse, summary, these belong to a time where RStudio or positron did not exist. Back when RStudio didn't exist, we would like get a quick glimpse of our data set using these functions. But nowadays, because we have powerful IDEs or integrated development and environments like RStudio and positron or VS Code, Virtual Studio Code, all of these things have become so much easier. But, you know, me being a boomer, we used to do in our time, we would glimpse data, click run, and it would just create an output of how many rows, how many columns, what are the country names, what are the series names, so on and so forth. Now, I want to get your attention here. Notice that country name, series name, years are coded in such a way that there is a backtick. This is not a quotation mark. This is not a single quotation mark. This is not a double quotation mark. This is what we call a backtick. In the previous lecture, I explained to you what these are. When we are referring to the uh, variable series code or variable country code, country name, or the years, we have to use the exact backtick. So fun times, my keyboard has no backtick button. Your keyboard probably has a backtick button. Find it, save it, take care of it, take good care of that button. I don't have it. But in the following commands, we are going to be referring to these variables with the backtick. So probably I'll go online and find a backtick symbol, copy and paste it like a newbie, but it's okay. I hate teaching a perfect code. I just want to create as many problems as possible so that we can um, work on them together. Then we can also use summarize, not summarize, summary. Is summary? No, summary. Yes, data. We can also use the summary function. We run it. That is again, if you have taken my Excel course, IR 202, in Excel, we have what is called descriptive statistics or summary statistics. It gives you the statistical distribution of the data. So it says country name, country codes, class character, mode character. For every single year, it shows you the minimum value, first quartile value, median value, mean value, third quartile value, max value, how many not available values there are. And it does the same thing for 61, 62, 63, all the way down to 2024. And now I understand that my latest value is not 2025, but it is 2024. Now, what is this? E is an exponent designation, and this is scientific notation. It basically says that 1.604 after this value, there are 8 other numbers, if you will. So it basically gives you an idea of whether this is a million, tens of millions, hundreds of millions, billions, tens of billions, hundreds of billions, trillions. So this is scientific notation. It gives you the first four numbers, and then it says that after this, there are 13 other numbers. So this is actually a very long number. It has 13, 14, 15, 16, 19 numbers. So off the top of my mind, I don't know whether a 19 range number constitutes a trillion or a billion. I have no idea. But long story short, these are not errors. It basically gives you how many other numbers are there that follows this. So if, of course, this has 13 other numbers after this, it is a bigger number than this one, right? Because it only has eight, probably like something billion. And then this is something 100 billion, right? So this is something trillion. This is simple scientific notation, which is in order to save space, it gives you the first four numbers and then it says how many other digits exist. I've been saying numbers, it's like digits, how many other digits that exist afterwards. It's scientific notation essentially. So it's good to have a general glimpse of the data that I'm working with. So then in my second operation, I can do things like select a single indicator to describe GDP. Not maybe, no, filter a single indicator because I'm going to use the filter function. So now that we have imported our CSV data, we had a general sense of what it's trying to tell us, median, mean, first quartile, minimum, maximum values. Now, I would be interested in doing some kind of analysis, some kind of visualization, and I will be filtering an indicator out of this general Y format data that I'm using. And filtering, mutating, formatting, cleaning data is usually the most important first steps. Some of the best data scientists, they usually spend about 90% of their time data cleaning, data formatting, data wrangling, if you will. If you can do these things well, you can do data visualization relatively easier. So let's create an object called GDP and let this GDP extract a specific number of values from the data that I'm working with. And while extracting a simple, like single indicator, let's also pivot this wide format data into long format data. I'm going to explain to you what this means specifically. So GDP is going to take a command, a series of commands from data. And remember our pipe operator, it comes from a Magritte R package. It basically chains multiple commands to each other so that you don't like run every single time. It basically connects everything. And notice that after this pipe operator sign, when I hit enter, it is going to start with an inline indent, meaning that R understands that anything that I'm going to write after this point is going to be linked to the code that lies above. So first, I'm going to use the filter, keep rows that match a condition. I'm going to take rows and parts, chunks of my data that fits a certain criteria. Now, I'm going to take all rows where My series name is going to be, let's scroll up, 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 up. What is the exact and precise designation? So it has to be GDP current US dollars. So my series name has to be this. So what I do is that in the absence, because I don't have these backticks, I'm cheating. It is no, it's not series code, it is series name. So I'm going to copy this. I can type it as well, but my keyboard doesn't have backticks. It's like nowhere in the layout do I have them. So I'm going to cheat. I have taken these using the series names. You can also in Mac or keyboard, you will have a keyboard layout uh, thingy. You can look at your keyboard. So what this does is that it looks at your keyboard layout because you might be using different keyboards, external keyboards, like I'm doing. Not maybe all of you are working this on a laptop. Maybe some of you are using a desktop, which has an external keyboard. And it basically shows you the layouts of your keyboard. So it says that normally backtick should exist on my computer. But guess what? Oh, sorry, I have green screen. So the problem is in the place where it is supposed to have this backtick, I just have a longer shift button. So the layout that it sees of my own keyboard is actually wrong. I don't have a backtick. But for you, if you can't find a backtick, what you can do for any, like the tilde function here as well, you can open up a keyboard um, layout thing. You can use that. You can go online and say things like backtick on Mac, or you can say backtick and it is basically going to give you this. You can just copy this and paste it into R. Backtick is not something that we use very frequently. We basically use this because I want to refer to a column name specifically, and I need to refer to it in the way that R sees that. And here, because I'm not doing a mathematical operation, I am using a conditional. It's going to take a while until you understand these things like very precisely, but I'm not doing a mathematical equation or a mathematical operation. That's why this equal sign is not useful for me. I need a logical equal sign, double equal sign. It has to fulfill a certain function. It has to refer to a specific item. I'm not saying 2 plus 2 equals 4. Series name must be GDP current US dollars. Exactly. You can type this if you want. You can copy paste this as well. I like copying and pasting because you have to refer to these things clearly in the same way R sees these things. So it's usually preferable to me to copy this and then copy this and paste it here. So the series name has to contain GDP current US. So I'm basically extracting everything that fulfills that criteria. Series name, GDP current, take them all. Now I'm continuing with my pipe operator. My command is not over yet. Remember last lecture I talked about wide pivots, long pivots, wide format data, long format data. Here I'm going to convert this into a long format, which is going to be conducive for doing line graphs, time series analysis graphs. For that, I need my data structured as a long format data. So I need to use pivot longer. Now, this command is going to be a little bit verbose because for you to be able to pivot something longer, you first have to specify columns. So if you are going to take certain columns, what is the actual criteria that has to go into actually taking what should be the format of your columns? So columns in this context, there are multiple strategies. So what I'm trying to do is that I need to take all these series name columns and I need to take 60, 61, 62, 63. But the problem is I also have this YR 1960 thing as well. So uh, I can specify a range, or what I can say is um, it's really a matter of taste, but I usually say starts with anything that starts with 19. So it's in all of the 19 years in columns. Notice your 19s in years are 60, 61, 62, 63, but then you also have to do starts with, you have to also do 20, and that's 2000, 2001, 2002, 2003, and so on and so forth. The only problem is that these two things have to be separated by this tab button. Let's see if my keyboard has a tab button. Okay, so in my computer, I clicked Shift and then clicked wherever I see this tab, and this is the tab um, function that you are looking for. So column starting from 19 starts with 20, and then we are continuing. Sorry, we are continuing with a comma, not a pipe operator, because the pivot longer command is not yet complete. We have names two, a character vector specifying the new column or columns to create from the information stored in the column names of data specified by columns. So what should be my names be? Let them be years, because all of these numerical 1960, 61, 62, 63, blah, 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 they have to be stored as years or year if you want. And the values contained a string specifying the name of the column to create from the data stored in cell values. It is going to be these values, the GDP values that we have. We haven't removed not available values yet. We only specified not available values as not available, but we haven't removed them yet. So all of these values should be stored as a value. And then the pivot longer command ends with this parenthesis. So this parenthesis belongs to pivot longer parenthesis. And I am continuing with another pipe uh, operator because I need to do a mutate function. Mutate creates new columns that are functions of existing variables. It can also modify and delete columns. I'm going to mutate the year column. I need to parse this as a number because I'm using years. R needs to understand that they are numbers. It shouldn't treat them as string, because if I don't force or coerce a number as a number, sometimes R doesn't understand that they are a number. And so it doesn't really understand what I'm trying to do. And I'm going to do the same thing for value, in which case they have to be coerced as numeric so that I can accurately and properly take the desired values into the new object that I created. Assuming that I haven't made any mistake, I am basically selecting the latest code that I wrote. Okay, I haven't made the mistake. I make a lot of mistakes. Mistakes, it's not a problem. When you have error, when you have mistakes, you just know that even the best people make mistakes. They try to understand what the mistake is. They study the error code, look for information online, and try to solve it. Now, look at our data here. Country name, country code is white format. Now look at the same data. Afghanistan country code, year, and value. Because Afghanistan's values are not available, it starts from 2000. So it's basically the format, the structure of the data set got converted from a format that is easier to store and send and get a glimpse to a long form that is more conducive to do longitudinal analysis, meaning time series analysis. This is more conducive for time series analysis. Wide form, this one, the original one, is good for storing the data. We use both data options for different purposes. Now, in the third part, I am going to create some basic descriptive statistics. So what statistics do I have? I basically have values. I can only do value um, descriptive statistics. So I would basically say summary from GDP. So this GDP is this GDP, the object that we created just above. From GDP, dollar sign. What is the dollar sign? Dollar sign, you might say, why is a dollar sign? Is there no other meaningful like symbol? No, my friends, there are none. Dollar is the most meaningful way of referring to a variable within an object. I don't know why. I mean, it probably has a history from R programming language history, S programming language history, but in order to refer to a specific column of a specific object, we use the dollar sign. And here, I'm trying to refer to GDP's value column. So I need to take the values from that value column. So when I go and say GDP dollar, it says in that GDP, I'm observing 1, 2, 3, 4, 5, 6 columns. Which one do you want? And I'm going to say I want the values. So when I run this command, it basically says the minimum value of your values column is this, the first quartile is this, the median is this, mean is this, third quartile is this, maximum values. And then there are 2,556 not available values. You can also do mean. I mean, we already have mean from GDP, from dollar, again, from value. But notice that we have 2,556 not available values. It's going to disrupt our findings because what we have to do here is not available, remove. True. So if you see any not available values, remove them. Not available, remove. True. And then give me a mean of this. And it says this is the mean value of your data. You can also say median and do the exact same above. Copy, paste. Mean of values, median of values. If you don't know what these are, look at my Excel training videos where I explain to you what these are. Standard deviation, again, SD, copy, paste. What is the standard deviation? This is the standard deviation. Our world is wildly unequal. So differences in GDP between countries are super unequal. What is the range of your data? Again, pasting the same thing that I uploaded above. So this is, it says the range from this number with 6 more digits after this to this number with 13 digits after. It's a very wild range. But so basic statistics. You can also do things like mm, descriptive statistics by country. This would be a new object called GDP country stats. No. This is such a new keyword, I can't find anything. We are going to take GDP with a pipe operator. We are going to group them by country name. And I again need to use the backtick. My keyboard has no backtick. So I need to find country name, the backticked version, copy, paste. Um, I'm going fast and I'm talking a lot because I'm basically teaching for people who have never done these things. So if you're taking this course coming from an advanced statistics background or a Python background, if you find this like too basic, that's how it's supposed to be. The course is designed for people who have never done this before. So I have to be slow, I have to talk a lot. So um, and I have to explain everything like super high detail because for a lot of people, these are just like very new things. Group by country name, and then summarize mean GDP, which is, if I can find the equal sign, it's going to take the mean. I already, well, let's write it again. Mean, open parentheses, value NA remove true. I'm removing not available, remove true in each occasion because those NA values, they're not numerical. Uh, and because they're not numerical, they may generate an error. When R tries to process numbers with non-numbers, it just gets confused sometimes. So I'm trying to just remove not available values. In the same thing, the exact same thing that I did above, median GDP. Um, it's going to refer to median. I can copy and paste this value. I'm hoping I'm not making a mistake while copying and pasting so much, but standard deviation of GDP is going to be numerically equal because I'm using single equal sign because what I'm trying to get R to do is a mathematical operation. It's going to calculate. But if I want it to refer to a specific variable, I use double quotations. But when I'm asking it to perform a mathematical operation, just one single. Because on the other side, we have mean, median, mathematical calculations, right? So standard deviation operation not available, values true. Oh, what else do we have here? You can do things like minimum GDP, min GDP. It's going to be equal to the minimum of the values and not available should also be true. Maximum GDP is going to be max value parenthesis 1 So, okay, I added too many parentheses. So one parentheses closes this one. The second parentheses closes the summarized parentheses. Anything before is connected through pipe operators. I shouldn't have made a mistake. You never know. Let's click run. Okay, it created some warnings, but no errors. So it says that there were just six warnings, six operations that I couldn't uh, finalize. But beyond those six operations, we have GDP country stats here. So this, for each country, calculates their mean GDP based on available years of GDP values that they have, median values, standard deviation values, minimum values, maximum values. So such a success. You can always do head, return the first or last parts of an object. When you say head GDP country stats and run this, it is going to give you 6 by 6 tibble. A tibble is a more modern standardized way of a data table. Uh, in simple English, it doesn't mean anything. But remember, in the first lecture, I explained to you how our language is always like insider jokes, mnemonics, it's kind of remembering things in a funny and kind of twisted way. So a tibble is actually a table. It's a data table. It's 6 by 6 data table. In our language, it's called tibble because this is an open source project and people who are working on this are not really getting paid for anything. So they don't know how to do anything. Okay, five. Filter for latest year and get top 20 countries by GDP. So notice we are doing as many different types of data preparation, data summarization. These are bread and butter of data analysis. This is the most important part of data analysis. If you can do these parts easy, and if you build um, experience in doing these things, you're going to have a much easier time learning more advanced operations. To me, teaching data science, learning data science, the first few steps always have to be, of course, the technical side, because in the theoretical side, you also have to like generate theories, knowledge, how to incorporate social theories into data science. That is something else. But in terms of technicals, importing data, cleaning data, formatting data, wrangling data, so important. And if you come across another good data scientist, another data scientist will tell you exactly the same thing, like data cleaning, data preparation, properly importing something, understanding the data structure, converting wide format data to long format to wide format. So important. Okay, let's pick up the pace um, a little bit and let's have time for the fun bit. I'm filtering for the latest year and I'm trying to get the top 20 countries by GDP. I do that by creating a new object called GDP top 20. And then I am getting my GDP data above using the pipe operator. One of my students asked, why are you using not the native pipe, but the Magritte R pipe? Because I do not have this like tab uh, function, tab keyboard in most of the keyboards that I work with. So doing like the Magritte pipe is actually easier for me. But of course, like you can use any pipe you want as long as it's the correct pipe. That's such a wrong thing to say based on Magritte's principles because we know that it's not a pipe. Anyway, filter year has to be exactly 2024, the latest year. And then these have to be arranged in such a way that it is descending. And while descending, the descending data has to be the value in my data set. That's what is descending at the end of the day. And then slice head, basically slice the head from the top. It has to be N20, get the top 20, and then you get the GDP, filter by year, the most complete year in the data set that we have. Take the values, these values, and then arrange them in a descending value, and then get the top 20 of this. So let's run this, GDP top 20. Of course, US, largest GDP, China, Germany, Japan, richest countries in the world, right? Turkey is 16th. Yeah, good. And then let's use ggplot because why not? I mean, a 20 country um, data in which United States and China will be a little bit like bigger. It's going to be a box plot. It can be like a vertical box plot, horizontal box plot. Create a box plot for the top 20 countries by GDP. How do we plot? We plot by ggplot. So ggplot syntax, there are so many good ggplot tutorials around that um, I can't create a better ggplot tutorial. I mean, if you want to know more about ggplot, I already assigned, I think, 5 training videos for you for ggplot. They're like the best. But nowadays, like when you search for like ggplot training, ggplot for R, you get so many good training videos. So I don't think it is. And Hadley Wickham himself has in his R4 data science book has so many examples. There's no need for yet another ggplot training and tutorial. So I'm not going to do that. So what are we ggplotting? We are ggplotting GDP top 20. We are trying to convert this data frame into a box graph that is going to show us in a nice visual setting. Now, the aesthetic function describe how variables in the data are mapped to visual properties of geoms or geometric functions. What is the x value? What is the y value if you have a three-dimensional, if you're building a 3D model, what is the third dimension? Where is that data going to come from? If you're creating a GIF, a moving image, for example, in 3 dimension, where is the t value, time value going to come in? So what we need to do is that we have to specify that x is going to be a reordered version of country name, reorder country name, but it's once again going to take backticks. So I'm cheating once again. Country name, copy, reorder, paste, country name. Because I don't have backtick on my keyboard. Value, and then y is going to equal value as well. Now, ggplot has a different syntax. It doesn't really use pipe operators or comma operators. If you want to create like code paragraphs and link chunks of the code in a ggplot setting, we use plus. We go with plus. Now, geom, when you say geom, it is going to give you all of the data visualization options embedded in ggplots. Any popular data visualization tool that you can think of, ggplot has it. That's why we love ggplot. So I'm going to create a column, a box plot, a column bar, which is geom col. And then you can determine the fill function, but it's not the parenthesis fill function. It is the equal fill function. You can say blue. You can say red. Sorry. Oh my God. Different keyboard. I keep making mistakes. You can say red. You say yellow. You can say dark blue. You can say dark green. You can say dark orange. Is it a thing? Yes. Or we have in computer science hex color codes, HTML-based codes, in which any color hue that you can think of, so I want, let's say, something purpley, is going to have a hex code. Any hue, any darkness, any, it's crazy. And I would say, like, get a nice color and copy this hex code and paste this, but with a hashtag. So if you say fill this, it is going to fill in the insides of the column that you're using. So we're creating a column graph. Is going to fill the inside color of this with the color that you get from a hex. I think it's very, very cool. Then we go onwards. Labels. So any data analysis, any data visualization thing has to have labels, which should consist of a title. And in this case, it should say top 20, no, sorry. Okay. Top 20 countries by GDP, because that's what the data is. And it should say things like the x-axis should say country, the y-axis should say GDP, current US dollar. Labels, so labels also ended, and then theme. So there are also preset graphical themes, graphical settings, if you will. The gray, light, line draw, minimal, replace. You can play with all of these to see what each of those, the black and white, classic, dark. Let's say dark. I don't know. I don't remember what dark did, but let's run this visualization. Oh, it does this. Okay, so yes, United States could, but as you can see, country names in the x-axis are just like getting inside one another. This can be solved two ways. I can either put one country's name on top, the other one slightly below, but if I have a country name that is just too long, that is not going to work as well. So my solution, write after the geom fill, before this is connected to the labels code chunk, I add chord flip, which is going to get your x values, put to y, take y values, put to x. So flip the coordinates x and y. Now look at how the coordinate flip function is going to change this. Yes. So now I have a relatively legible, um, good, nice um, graphic in which it basically shows me what is going on, the top countries by GDP. So this is just one way of doing data visualization. So what is another way of doing data visualization? Now remember, in my Excel courses, we also do line graphs, um, which allows you to compare countries to one another, whether Spain's GDP is increasing at the same rate Turkey's GDP is increasing, and is it increasing in the same rate as of United Kingdom, for example? So what I can do, I can also um, create a line graph from a smaller number of countries and uh, filter for selected countries. Mm. Let's create an object. Why is this indenting me all the time? Anyway, what we can do is that we can create an object called selected countries, which is going to contain a vector of countries, let's say from here. Let's like compare Turkey with other countries in its own range. So let's take Poland, let's take Switzerland, let's take Netherlands. I'm adding a comma, hitting enter so that it indents. I'm trying to fit this code into the screen so that we don't have to scroll right too much. Saudi, sorry, Saudi Arabia. Um, Turkey. So it doesn't have Ü, right? It's just Turkey. Okay, Turkey. And sorry, I forgot to add Indonesia. The good thing is that I'm going to visualize this. If you want to look at different countries, you can always change the countries in this vector. So you can change the contents of the selected countries vector. So I have my selected countries vector, a vector that contains six comma separated values that are characters or string values. Good. Now we do GDP selected. We have to extract the GDP values of those countries. GDP um, filter. Oh my God, had to get country name. I don't have backtick, guys. Okay, filter country name. First, this is a new um, command. It's the pipe in function. It is basically, it's going to take everything related to country name in the selected countries object we created above. So GDP selected, take the GDP values. So this is what we created. We created countries, country names, their years, their values, but only for the selected countries that we have here, right? So now we are going to create a, a line graph, which of course it starts with ggplot. What are we ggplotting? We are ggplotting this time GDP selected, only 6 countries that we want in a line graph. So it's GDP selected, AES, again, in ggplots, aesthetic functions are absolutely critical. X is going to be year because again, y-axis, x-axis, if you want to look at the increase and decrease of something, x-axis should always be year or time. If you're measuring months, months. If you're measuring dates, dates. If it's time, time. It's year, year. So x has to be year at all times. Y has to be the value, the GDP value, value. And then this is going to be a line graph in which there will be 6 lines. In order not to mix up each line, we have to color each line by country name. Copy this again and paste it. This country name. Plus. And then what is the geom line? So it is going to be a geometric line graph in which how thick should be the line be. Play with different values. This takes a numerical value. The bigger the value, the thicker the geometric lines are. If you do 2, it's going to be, I tested several options before recording the lecture. 1.2 looks fine because it's going to be a dense graph. Geom points, every single year has to correspond to a point, and that has to be the size of 1.5. Labels are important. Title is going to be GDP current US dollars of 6 countries over time, or time series analysis of 6 countries by year. Doesn't matter. Subtitle, if you want to add, what these are, you can say, so Poland, Switzerland, Netherlands, Saudi Arabia, Turkey, Indonesia, and Spain. Don't forget the comma. X-axis has to x-axis has to show year, and then y-axis is going to be GDP current US dollar. Is it 2024? So GDP current USD. No, this is a time series. It contains all of the country, all of the years. Yeah, sorry. GP and comma, don't forget the comma. The color is in this label, in this legend, is going to be the country. So each color is a different country. Close the parentheses. My code isn't over yet. The ggplot craziness continues. Pick a theme. Gray, lights, dark, minimal. Minimal is always better, especially if you're doing data analysis. Everything else should be like very minimal so that the actual graphic, actual values should speak. If you make your theme like just way too colorful, way too complex, just for the sake of like aesthetics, it's going to take away from the fact that we are doing this so that we communicate information. Let's do theme minimal. Um, Continue. And we can change aspects of the theme. For example, we can say plot, title. We can make the title text bolder, for example. Element, text, face, bold. So if in Excel terms, we are changing the title and just clicking bold on it. But of course, in both Python and in R, these things have to be clearly specified. You can't just click on things. Everything has to be very precise. Axis, text, X is going to, I need to change the angles to 45 degrees. Let me show you how that is done as well. Element, text, angle, the angle of the text, 45 degrees, which is going to be like this. Every year is going to be diagonal. If I do 90 degrees, then it is going to take a lot of horizontal space. If I do like 0 to angle, then years, because we have so many years, the text might overlap with one another, and I don't want that. Angle would be 45, and then horizontal justification, whether it's left leaning, right leaning, or just like fully justified at the center. I want it fully justified at the center. Um, Good. I don't see any errors. If I have any errors, then it's going to show me. Run. Whoa, nice. So this is the graphic that we have generated every single time. Look, there's a zoom button here. You can, mm, the more you adjust, the more it kind of fits its contents based on the screen that you give it. Indonesia, Netherlands, Poland, and Turkey. Uh, Here, the general GDP is like really skyrocketing. I don't want to get into political discussions. Is Turkey's economy going well or bad? I don't know. I'm just teaching R. But you can basically interpret these is that, Dutch economy used to be like the best, the most like highest GDP. And then other countries, Turkey caught up, Indonesia caught up. Is Indonesia the biggest in our list? I think so. No? Yes? GDP selected. GDP top. No. It should be. Oh, Spain is not visualized. Did I not get Spain? Where's my data visualization? Oh my God. I lost everything. Okay, here it is. Yeah, I don't think I got Spain. Okay, it makes sense. I thought I got Spain, but no. In that case, yes, this shows you the correct latest figures. The largest GDP country right now is Indonesia, and then we have Turkey, at least in the list. We have Saudi Arabia here, and Netherlands here. Remember, we coded that labeled each country by color. Saudi Arabia, Switzerland is about here. Um, Poland is less. But of course, like nominal GDP is one measure, GDP per capita. Of course, some countries in this list would appear much higher if we did GDP per capita. Um, but now looking at this makes me think in the lecture part of today, I explained how correlation is something that I'm going to show you today. What can we correlate here? We can correlate the pace at which multiple countries increase their GDPs, and that is measured by year-on-year uh, measures. So 7, create that. We created that. 8 is going to be create a correlation matrix. Good. Um, so we have to now convert pivot longer back to pivot wider because for correlation matrix to work, I need wide format data. And that would be like GDP wide. Oh, from GDP selected, select the year and cheating again, getting the country name from here. And value, take those numerical objects, group them by, once again, country name and year, and then summarize by value, extract the first, last, or the nth value from a vector. I'm getting the first value from my GDP values list, and then summarize the data frame using the groups function. Uh, drop is a value that shows you anything that doesn't conform to this criteria has to be dropped. And then pivot wider, get the names from, if you're going to take the names, the object names, the variable names in the columns. Country name, get the values, names from country name, values from value, not value, it's value. And then arrange them by year. So hopefully this works. It works. I still have not available values, so I would probably have to clean data. But of course, Poland not available values is from the Cold War period. But I converted the GDP selected. Why are you not showing me this? Okay, I'm converting the logic of GDP selected, which is a long form data, into a wide form data. I'm taking long and then converting it back to wide. And if in correlation matrices, uh, not available values are bad. So what I need to do is I have to drop countries with fewer than 2 non-missing observations. Um, and now GDP mat is going to be GDP wide, in which select year. So this is GDP mat. The year is gone. I don't need years because I need these correlation values to correlate with each other. I don't want the numerical values to also correlate with years. I don't want $1.5 billion to correlate with 1984. So that's why I am dropping years. I'm also dropping, not May, it's maths. GDP math. Here, bracket, because I'm going to do refer to a specific part of GDP math. Comma, when you put comma, this part are observations. This part should be the variable section. So I'm not doing anything in the observations. I'm changing the variable section by col sums, form row and column sums, and means for numeric arrays. I'm basically doing calculating means out of this. But in this, is not. Remove all not available values in GDP math. And then this condition has to happen more than one. Otherwise, do not drop. Let's look at what this does in GDP math. It is basically summarizing columns based on the criteria that I have added. Now, this is suitably modulated in such a way that I can calculate correlation of GDP levels. And this is a new object called correlation levels, in which correlation covariance. So core comes from the statistics package of R. Core GDP math use. So the core function, I haven't mentioned this specifically, but you would notice that R gives you hints and tips. Core X is the data, Y null, use everything. And in that sense, method would be either Pearson correlation or a Kendall correlation or a Spearman correlation, which is all different famous statisticians. We are going to be using here pairwise complete observation method. If you want to know how to input correlation methods here, you can go and read the documentation of R's correlation package, R correlation package correlation. So here you are going to notice its reference manual is correlation here, package correlation. We are using this package. And essentially, every single time you encounter a new package, you basically go and read its documentation. And different types of correlation, Pearson correlation, Spearman's rank, Kendall's rank, bi-weight correlation, percentage, Bloomquist, gamma observation, Gaussian rank correlation. So it basically gives you different correlation types that exist in its ecosystem. Then you would do methods. Which methods are you going to do this correlation? My correlation is Pearson. Let's see if I made any mistakes. So correlation levels for GDP on this paper. Okay. So because this is not a table, it is just giving me oh no, it's actually giving me the correlations as well. Which country correlates with which other country? So actually my kind of graph is mostly okay. Correlation levels wise. So you can do print round up core levels, the object that I created above. Don't forget to add the latest thing. Oh, it just says 1111111. There is probably no core levels because it has to be bivariate. I have to add 2 here. Because if I don't add 2 here, it's just correlating each country with itself. Now, when I say 2, it is doing this with others, not itself. And these are, very highly correlated. But this is not really the thing that I want. What I want is I need a correlation of year on year or YOY growth rates. So it's basically percentage change of the GDP growth. So that would be a new GDP growth would be GDP wide. Arrange these by year and then mutate these columns across in a declining fashion year. And in order to be able to do year-on-year measurement, I need to use the lag command. And this is going to be funny because I need the tilde sign, the twisty, squidgy thing. Is it here? No. Is it here? No. Is it here? No. Okay, where's my keyboard layouts? Keyboard layouts. Keyboard layouts. No, not that one. Keyboard layouts on Mac. Okay, this is ABC. Let me show you. No, this is not what I want. Set a change keyboard type. No, keyboard shortcut. Do nothing English. Okay, once again cheating. The sign I'm looking for is tilde key or tilde sign. Yes, it shows it's there, but it's not actually there. So tilde sign. Okay. So it's the wavy sign, the electric boogie designator. Copy tilde, paste tilde. Yes, thank you. Tilde operator allows me to add further conditional in statistical operators. So I will be doing something like minus lag, which basically calculates the percentile rank of year-on-year measurements that I'm doing, divided by lag, once again, multiply by 100, but multiplication sign is not X. Where is the asterisk? Here is the asterisk by 100. So in every year section, in every column and variable that is not the year section, we are doing a year-on-year calculation. How much has it increased on a percentile value? Out of 100, what was the GDP growth rate? And basically do this operation across all years. GDP growth. So these are the GDP growth rates year-on-year of countries. Some countries have declined so much, some countries have increased significantly. Good. I can do a better correlation map out of this. So now correlations of growth of countries is what I'm after. This is going to take correlation of GDP growth, but I don't want years because then it again starts to correlate the numerical values of years with the numerical values of year-on-year increases, which is going to give me the wrong results. Use pairwise dot complete observations, and the methods will be our dear Pearson. Oh my God, I'm so tired. Anyway, run correlation growth. Okay, these are how much each country's year-on-year GDP growths are correlated with one another. Of course, Indonesia, Indonesia, Netherlands, Netherlands, Poland, Poland. These are one Pearson correlation because it is the same data. Poland's correlation with Poland is perfect correlation. And you would notice that all of these one values are the same. We are interested in Indonesia, Netherlands, Poland, Indonesia, Saudi Arabia, Indonesia. We have to actually modify these, you know, pairwise, one by one correlations. So this would, for example, be print, round, correlation growth, not with each other, but with other countries. And then you're going to get a much nicer and meaningful thing. So remember, we are going to be doing a correlation matrix. It looks like a ladder. So there is a specific package in R that is designed purely for correlation plots. In order to install it, I'm heading to the beginning of the session because you should always see which packages you have installed and which packages you have added to the library at the very beginning of a project. The bad part about going and installing something in line 111 is that it's very difficult to keep track of what has been installed. So here, I'm going to say install packages. The package that I'm after is grammar of graphics, correlation, plot. This is just a package that R makes it very easy to produce correlation plots, graphs, interactive ones as well. And then I add to the library, GG core plot, and then now I can come down and visualize the correlations. GG core plot. What am I core plotting? Correlation levels first. It's not going to be meaningful correlation. You're going to see why. Do you want labels? Yes, I want labels. Do you want, what label size do you want? Try one, try two, try three, and see which one is going to be better. Type of the label, is it full or lower or upper display? I have no idea how the labels are going to appear. Let's say lower. If I don't like it, I won't use it. Colors. It needs to get a vector of different colors. Again, you can go red, blue, white, whatever, or you can use hex codes. My suggestion, let's use very distinguishable ones like red, yellow, or green, and blue. You can always, again, use hex codes if you want. If you want like very precise, very specific colors with like hues. And a title for that is going to be correlation of GDP levels across 6 countries. And there has to be a theme, GG theme. Um, theme. Again, the ggplot themes that we used before applies here as well. Let's I, minimal. Let's do minimal. I don't know why. I just like minimal. Ggplot, correlate. Okay. So this is a correlation plot that might look interesting, but it is very practically meaningless because on a scale of Pearson 1 to Pearson -1, all are very highly correlated with each other. And that is not very unexpected because in the previous one, we already know that they are basically increasing largely together. So it's not, what's that? Good deficit GDP. I mean, it's very straightforward. What is more interesting is not plotting correlation levels, but correlation growth. So instead of levels, growth. I'm going to do correlation growth instead of correlation levels. I just changed the measurement. Instead of correlation levels, I'm using correlation growth, which I calculated here before, the year-on-year increases. That is going to give me more information about countries' tendencies. And red is number one, like perfect positive Pearson correlation. No, blue is perfect Pearson correlation. Green is something in between. Red is minus. So maybe yellow be a better way. And title correlation year on year changes. Correlation of GDP year on year changes across 6 countries. And everything basically remains the same. Now, look, this is just basic, yeah, factual correlation trends, and it doesn't give me much information. Everything is so correlated here, but this is going to give me a lot of information. Now, look, now we have a meaningful thing happening here. Let's zoom in. We now have actually good information about, for example, Netherlands and Switzerland. Their year-on-year increases are very similar, probably because they're in the euro trading area. Same thing for Netherlands and Poland, but not for Switzerland and Poland. So probably Switzerland and Netherlands are very close trading partners. Poland and Switzerland rather more. So EU countries, if you will, are very much correlated. When we see Turkey has the highest correlation of its GDP increase with Netherlands, probably because they're main investment and trade partners, followed by Poland, followed by Saudi Arabia and Switzerland. Least correlated is Indonesia. It's an entirely different region. Makes sense trade-wise, investment-wise. It's very, very far away. But so the correlation between GDP year-on-year growth here give me a lot of information about how countries in the top 20 GDP uh, are likely in terms of their GDP increases. This is a significantly more meaningful and informational graph compared to the previous one, which really doesn't show. It's not like it doesn't show anything, but it doesn't show things that I want. Good. So this is basically going to the World Development Indicators, getting CSV, importing, cleaning, formatting, long to wide, wide to long, and then doing calculations, doing top 20, visualizing that as a data visualization, doing correlation analysis, converting that into a correlation table, So this was the CSV part of the lecture. Now, in the next part, we are going to be getting data directly from world development indicators using an API and creating interactive visualizations, not like the static ones that we created using ggplot. We are going to be creating JavaScript-based interactive moving visualizations, and we'll start that just after this. So get tea, get water, and let's come back in several minutes. Hello, welcome again. So this is the third installment of this lecture we've gone so far. Hopefully, this is going to be covering most of the gaps that I feel the class, has had in the class. So in this session, we are going to complete the cycle. So this is going to be a session in which we're going to use World Development Index API in order to get data. We work with CSV file. Now we're going to work with the API thing. And I mean, given this is intended for newcomers to computational social science, you've already written more than 100 lines of code. So the more you write code, the more it's going to be easier for you to follow coding lectures, and then gradually you'll be able to write your own code. So now what we're going to do is we are we are going to use World Development Indicator API to get data. For this, we are going to need the install packages World Development Indicators. Now, so what the World Development Indicators, yes, why is it restarting? I have no idea. But in any case, the reason why we are downloading the World Development Indicators package is that it allows us to automatically get data from World Development Indicators. So notice last time we selected what we want, we downloaded as CSV, and after CSV, we worked on that CSV file. With World Development Indicators, we are going to get data in JSON format, JavaScript object notation format, and we'll be working, on the actual data stream that we get from the World Development Indicators. So in order to know World Development package for R, package WDI. In order to know what any given package wants from you in terms of codes, in terms of syntax, you already know that you have to read the documentation. And so the usage of the World Development Indicators package is that you use the WDI code, and then if you want all countries, you write all. So I understand now that, if you want to use World Development Indicators package, the syntax goes WDI country all. Okay, what does it want from countries? Vector of countries. So ISO 2 character codes, not like ISO 3 ones that we used in the CSV file. So Brazil, United States, Canada has to be ISO 2. Indicator. It wants indicator as codes. So character vector of indicator codes. See the WDI search function. If you supply a named vector, the indicators will be automatically named. So see women private sector equals, okay. Start date end date extra true returns extra variables such as region, ISO 3 code, and income level. Cache, a list created by WDI cache to be used with the extra true argument, latest language. And basically it gives you several examples of which this package works. All packages that you will be working with, you should always read the documentation if you're serious about data science. I highly recommend you to read the documentation of tidyverse underlying packages. So what we do right now, I need to make sure that tidyverse, ggcoreplot, and WDI, they all work and are introduced to the library. And the first thing I am going to do is that in the previous exercise on CSV, we work with GDP, gross domestic product. Let's download multiple indicators and multiple variables. So let me store these indicators in a specific object called indicators, which is going to contain a vector of indicators. For example, what should we download? WDI search. What if I say military? Let's see what we have about military expenditure. Okay, it has how many? 1, 2, 3, 4, 5, 6 indicators related to military. Military expenditure, current US dollars, military expenditure, current local currency units, military expenditure, percent of GDP, percent of GNI, military expenditure, okay, we need this, military expenditure, US dollars. So this corresponds to code 13154, 13154, the code that we need to get military expenditure in US dollars. Basically, how much that country spends on their military armed forces on that given year in US dollar terms. For those of you who don't know where these data come from, these data come from both national defense ministries or statistical institutes or independent observers like Jane's Defense or SIPRI, Stockholm International Peace Research Institutes. So here I need this as an indicator, but in order to simplify things and make it a bit more meaningful, I am going to call this by assigning this to a sub variable called military, so that every single time I want to call this statistic, I don't want to write this code, complex code, I just type military. And so I'm leaving a comment for myself here saying that this is military expenditure. Or let's not get this. Uh, I changed my mind. What I want is that I want to get military expenditure for all countries, healthcare expenditure for all countries, and education expenditure for all countries. Three indicators that I can properly compare. And the best way to compare these is by looking at their share of GDP. Because we worked with GDP before, and even, better yet, we can combine the data that we pulled from API with the GDP data we extracted through CSV, so that you can combine CSV extracted data with API extracted data, and it's going to be a much better exercise. I want military expenditure, not current US dollars, so this is not going to be a dollar figure, this is going to be a percentage figure. If a country is in a war, it spends more of its GDP on military expenditure. If a country is in relative peace, it spends less of its GDP to military expenditure. So I want this I want this. The corresponding number is 13156. 13156, the corresponding code is this. So I copied that, military. Okay, so this is going to be military expenditure. We can even copy this in case we forget. I have to put a comma here because notice, since I added a hashtag here, R is not going to run anything that comes after this as code. It's just a comment. So we continue here. Let's get education. What is the education code? So WDI research military, let's say education. Ooh, there are so many education related. Can I? No, I can't. I want government. See, there are so many education related indicators. I want government expenditure because that's the only thing I can compare with military spending. Scroll up, 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 up. Lower primary, second public, international. Sorry, I had to go down. Uh, there's so much international. Dates, coordinating mechanism. Uh, um, hmm. Education government? No, there's no such thing. Education government. No. Um, okay, I'll go directly to World Development Indicators and try to find it here. Education. Government expenditure on education. Total GDP. Okay, I'm looking for this. Government expenditure on education. Total percentage of GDP. Yes, let's look at I. It is this SEXPD total GDCS. Copy this, paste this, uh, comma this. To for better data science discipline, it is always important to write the extended names of the variables that you're getting. Health, what is health? The VDI search health. I hope it finds something. Oh, so much. Government health expenditure per capita. Government expenditure per capita. This health expenditure, public, health expenditure, total government expenditure, total public GDP. Is there anything that has everything? For total expenditure. It is far less straightforward to find it from here. So I'm once again going to do it from the actual WDI webpage, health. Current health expenditure. Yes, this is what I want. I yes. I should be able to find it from here as well. I don't know why. Good. I'm specifying the indicators, current health of GDP. Okay. Okay. So military, education, health, their corresponding WDI codes, they will all be wrapped as a vector and then introduced into indicators as an object. Because here's the trick. In the following codes, I will always refer to these indicators using this object. If I want to change my indicators, I can just change indicator definition, indicator code, but the indicator will always be here so that I don't have to write all of this once from beginning every single time. So, okay, let's run. It's okay. Indicators. I should. Oh, error in military education facility argument 4 is empty. Now, where have I made a mistake? Oh, here. Okay, this shouldn't be here. Okay, now fine. There was an extra comma that messed up uh, art. So indicators are here. There are three indicators. These are all character vectors. And let me clean this place as well so that it's just empty. It doesn't eat up my GPU. So now, goods. I specify the indicators. Now extract data from the VDI API. Now, this is the simplest way of um, using an API. Uh, because I don't need a key, I don't need a password. It just using the package WDI, it directly connects to World Development Indicators database and gets the data. It's, I think, wonderful. It is super helpful. So I'm going to World Development Indicators package. It says this is how you are going to use it. Why not copy it? Let's cheat. So WDI, country all, indicator, whatever, start, ends, false. Okay, but we have to change this a little bit. So I want all countries, yes, but indicator, this is only just one indicator used as a sample in the code book. For indicator, I want this, all the indicators I indicated there. So I have to say indicator is going to come from this indicators. Start 1960 because World Development Indicator goes all the way back here. And today, how do we do today? It is system date, but system date has to be specified. It has to be converted into a numeric object. So it has to be as numeric um, system date. But I only need the year from this. So it is going to be percentage year of the current year that we are working on. Close parenthesis for system dates. No, maybe not. So just only one single. Okay. Extra. I need extras because I need to drop aggregates. I'm going to explain to you what this is. I don't want cache. I don't want latest, so I can just remove them. Language, English. Um, let's see if this works. Okay, so now this is working. You understand that this is working because the code runs, but see, there's a stop sign here. It says stop interrupt R. Right now, it is connecting directly to the oh error. I forgot. Following indicators cannot be downloaded in area that arguments are valid. Okay, I made a mistake. Let's fix that mistake. The first mistake I did is I forgot to create an object, a basket in which all of these data are going to go to. So WDI raw data is going to contain all of this. So it's going to extract all countries, the indicators are specified, and is going to be our system date latest year. So if you are still watching this video in 2028, if so, leave a comment into the comment section. Uh, it is going to take the year of your system date, whichever it is that your system date. Um, oh, okay. Let's check this again in case. Please get my data. So it's hmm. Shining indicators. So which ones? So country indicators as numeric. The following indicators could do. So it can't download any of the indicators that I'm trying to download, and I latest version of the ATIs, latest usual. Um, is it maybe I have to just write 2025? No. Indicators, yes. These are my indicators. These are correct indicators. They are good indicators. Military expenditure, education, health. Sometimes the World Bank does serving. Okay, let's copy this to see if the World Bank is actually serving the data. Sometimes that's the thing with APIs. Sometimes services can be down. No, it is actually giving good data, my military expenditure indicator thing. So the problem should be my code, maybe, probably. Um, let's try again. For some reason, it's not responding to my API call well. This sometimes happens. I may be wrong. There may be a flaw in my code. Okay. If not, there may be a problem with the connection. It happens. Sometimes servers may be down. That also happens. I wonder what the problem is right now. Or, oh, okay. It was that I tried to use the fancy way of trying to get ISO 2025. Let's get the year of your system date. But probably, apparently, that was the problem. So now, WDI row, I have my data. Let's check my data. Nice. Nice. So nice. Afghanistan, military expenditure, not available values, not available values for Afghanistan quite a lot. This is long form data. Now, of course, after looking at my wide form, long form data, you understand what a long form data looks like, what a wide form data looks like. So we have country, Bhutan, because it's long form data, it's like year, status last updated, ISO 3 country code, ISO 2 country code, military expenditure percentage of GDP. So these are no longer dollar values, these are percentage values. So this means that this country, Bolivia, in 1978, used 2.3% of its GDP for military spending. Education, same way. Health, same way. Region of those countries, capital of that country, longitude, latitude information if we want to map this, income level, lending system. Lending means if World Bank is supposed to lend financial aid to that country, what is the mechanism, lending mechanism of that country? So what's left to do right now is to clean and reshape this data for the kind of visualization that we want to do. Clean and reshape the data. How is that going to happen? First thing, we have to drop aggregates. What are the aggregates? Aggregates are these. Um, so in country designations, countries are countries, aggregates are country groupings. If I only want to look at cross-country comparison, these aggregates muddle the waters a little bit. So if I want to look at the comparison between Hungary and Spain, for example, they're also in the euro area. So that their statistic also comes if I include the aggregate. So I don't want aggregates, I only want countries. So I need to drop the aggregates uh, and drop not available values. And this is going to be finally WDI clean data, which is going to take WDI raw, but it is going to first filter. Um, First, let's remove not available values. Critical note that when I use the API doesn't give me the two dot system that the CSV was using. It is giving me the not available values directly. It is much better. It's much more helpful for me because I don't need to specify like I did in the beginning. These are the not available values that are so I don't need to specify this or emptiness. It comes already with the API. So it's much easier for me. First thing I need to do, I have to drop all not available values in the region section. But also in the region section, I need to remove, this is the remove function, aggregates. It is going to get rid of country grouping so that I can focus purely and solely on countries and country grouping. Then I need to select certain columns, certain variables. And these are, I want country, I want ISO 2, I want year, uh, and military education health. And drop anything else that doesn't really serve my um, ambitions. So we're selecting country, we are selecting ISO 2C, we are selecting year, we are selecting all of the names. What names? Names of indicators. And indicators, again, are these indicators. So I want this, which corresponds to this. Instead of like writing three indicators, I want all of the names of indicators. It's slightly more economical way of coding. And then rename um, column names. Um, uh, I need to, let's do first heads, because I need to cheat again. WDI row. Okay. So, okay, it's not giving me with this. Let's do glimpse. Okay. Mm, it's still not giving me what I want. Um, okay, then let's do the ultimate cheat. Give me the back tick. Okay, copy this. My God, I really need to change my keyboard into a keyboard that actually has the backtick sign. So let's go here, new paragraph, military percentage GDP. This needs to be just renamed purely and finally as the military education percent GDP. This is going to be education. I'm renaming the column name so that it gets simplified. Health percentage GDP. Maybe there is one space in between. This space has to be here as well. Health, close parenthesis. Pipe. These have to be pivoted longer so that the columns include a vector of this, comma, this, comma, this, comma, of GDP. Okay, another comma here. Names two in the pivot longer. They have to go with indicator. Names have to be converted into indicator, and values are going to be converted into value. Pipe. Then we have to mutate assuming that I'm not making any mistake at this point, which I might. I'm writing a very long code, so it probably is going to say you're making a mistake at this point. So year is going to be as integer year so that it doesn't mistakenly recognize them as text value or string value. As numeric value again. My God, such a crowded looking code, but hopefully drop not available in all of the values. No, value. Oh my God. There so many things can go wrong with this. Oh, let's run. Yes, I didn't make any mistakes. Okay, what happened? WDI row, it removed not available values. From 15 variables, I only have 5 now, the ones that I need, the ones that are required for me to be able to um, do further analysis of this. And um, what we can do here is summary statistics by indicator. Summary statistics is very important. I mean, if you are doing your bachelor's, if you want to go to a good master's program, if your professor or lab manager is a data scientist, it would be useful for you to know how to produce summary statistics and summary values by indicator. So, description by indicator. This is a new object that I am creating. It is going to take the clean world development indicator data that I have, and it is going to group by indicator, not indicators, pipe, summarize everything, produce summary statistics. Number of observations, they have to be assigned to n how many N there are. Number of countries would be N distinct. I don't want to get how many times Afghanistan appears. Probably they appear like 70 times. I need distinct, each distinct occurrence of a country within the variable country. Mean is the statistical mean of the value, and then median is the median of the value. Standard deviation, these things are important. They may sound or look boring, but they're quite essential actually. The minimum value for countries, min value, max value. I don't want grouping structure of the result. So if I say drop, all levels of the grouping are going to be dropped. I don't need groupings. I just want to see these properly. So the summarize part is over, but my code is not over. I'm connecting this once again to the follow-up. Arrange these by indicator, yes. And then they're going to be summarized from top to bottom, hopefully, if I don't make a mistake. Yes. Okay, so for education, for health, for military, how many total number of observations I have year on country? How many countries are available in each data set? So we have more distinct countries, data fully available in only 163 countries for military, more for health and more for education, probably because military spending is a sensitive type of data. Maybe some countries don't really want to get their military spending data available. A mean of total education spending, median of education, median of all spending types, standard deviations. Of course, military spending has the most standard deviation. Minimum, interesting, some countries really don't spend on military, but then maximum, of course, military spending has an enormous maximum, which is mostly predictable. You can always, of course, do things like print description by indicator so that they also appear in the bottom console section. Usually when you are going to create line graphs, it would be important to know which years are available to plot, which years are available to do statistical analysis as well. So we could do yearly data coverage. So countries with available data per year. So this would be availability per, let's say, by year. This is going to get World Development Indicator, group by indicator year, and it is going to summarize the number of countries in which N distinct is country, and the groups will also be dropped because it's going to mess with my data output. So how many years exists total? Availability by year. So for education, for 1970, we only have 32 countries. It gets a little bit better and better and better, but it fluctuates. Yearly, some countries' education data is available. For some countries, it's not. Slightly increasing, increasing, increasing. I think the biggest jump is between 1997 and 1998. Suddenly 50 countries become available. This can be because data collection efforts of the World Bank, newer data collection methods, another jump in 1999. Healthcare, um, oh, it actually starts from 2000, so it doesn't go all the way back to 1960. And since 1960, it's pretty much out there. But a sudden drop in 2023, I don't know why this drop is there. We have to ask the World Bank. So military spending goes all the way back to 1960 and increased relatively smoothly. I think it's the highest coverage in between countries. Good. This gives us some indication about how many countries can we compare across years. It matters in things like if, like for those of you who are working on more intermediate statistics, if you want to do like regression discontinuity or diff and diff, these year availabilities matter quite a lot, and it gives you a better causal strategy if you want to pursue, time series longitudinal causal work. Now, I'm interested in plotting um, countries, no, top 20 countries by military spending plot. Military, military, top 20 uh, from World Development Indicators, filter, indicator. Which indicator? I'm not running a mathematical model. I'm not calculating something. Indicator has to be exactly, specifically military percentage GDP. Yes. Year, military. Year is going to be exactly 2023. I'm making a mistake. Okay, where have I made a mistake? So it says unexpected token. So here, notice military spending GDP, the single quotation has to finish after the paragraph. I mistakenly wrote it before, and it's still giving me an error, unexpected opening of the bracket, because my code is still not done. So pipe. Let's continue down. Sorry, I need to also, yes, close the parenthesis here. Okay. Unexpected end of the document. No, it's not an unexpected. No, okay. Arrange by descending value. Pipe. Slice head. I'm going to take the top 20 and equals 20. So I'm creating a new object called military top 20, getting WDI, filtering by indicator from military spending percentage of GDP. I'm using only for 2023, top 20 countries by military spending in 2023. You can change the year, of course. Instead of top 20, you can do top 50 if you want. Military, yes. Who are the top spenders? Whoa. Okay. So Ukraine, because there's war there, 36% of its military spending spent on military. Predictable. Lebanon, predictable. Algeria, probably predictable. I may not know what's going on. Saudi Arabia, regional tensions. South Sudan, civil war. Russian Federation linked to Ukraine. Armenia, probably because of the Karabakh War, Oman, uh, because of Yemen, Israel, Jordan, Kuwait, Azerbaijan. So all of these military spending is basically what percentage of that country's GDP is spent on military. If a country is spending a lot on its military in terms of not dollars, but in terms of percentage of its GDP, it means that there's something going wrong in that country or there's some kind of crisis in that country. But of course, we always visualize these things. So let's visualize GG plot military top 20. Uh, the aesthetics is going to be X. If I don't reorder, it is probably going to come out inverse. So let's reorder this by country and value, in which Y is going to take the value plus, no, plus. Um, this is more suitable once again for bar graphs, the column. What do you want? Unexpected end. It's not ending. Geom call, because it's a column, we need a fill for this. Pick a color. I don't know. Mm, 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 mm. Hex color codes. Should it be yellow? No, it has to be red. It has to be grim and dark red because it's military spending. Let's take this. You can pick any you want. Paste. I have to add a hashtag. It doesn't work without a hashtag. Okay. Ominous enough. Then labels. What would that be? Title is going to be um, top military spenders of 2023. X-axis is going to be country. Width Y is going to be percentage of GDP. Then theme classic. Okay, let's see what we're going to get. Okay. We have the same problem that we've run into earlier, right? These country names are just like squeezed. Even if I like maximize the horizontal kind of span of the screen, country names fall on top of one another. So I need to, just before labels, I need to do chord flip, which is going to take the x-axis and put it on the y-axis and put the y-axis on the x. I didn't like the theme. It's too simple. Theme. Classic dark. Let's get dark because we're visualizing something dark. It's military spending, right? So, okay, it's not that dark, but theme dark. Why is theme dark null? Do they not have gray, lights, minimal, replace, gray? Run. Theme minimal. For some reason, I'm getting interesting. I have no idea why this is happening. If you know why this is happening, just let me know. At the end of the day, the graph that I have here is correct. Top military spenders by percentage of their GDPs. So it's a pretty grim thing. But for example, let's do the same thing for education, right? So top 20 countries by education spending in, let's say, 2020 plot. This is going to be education, top 20, world development indicators, type, filter by indicator. It has to be exactly education, GDP, close parentheses, year has to be, no, sorry, the single quotation has to end here. Year has to be 2022. Type range descending value slice head, because we have to come out have the top n top values. So slice head, like the whatever, whichever number you give here, it's going to get that much from the top, basically, if it makes sense. Okay, education top. Oh, wait. Oh, so 2022. Maybe they don't have it. Why do I get 0? Nation top 20. Oh, maybe. Oh, because, okay, it is so specific. Education. So in these kinds of referring to a specific column and the column name, it is so extremely super crazy specific that even if you say education, space, parentheses, so there has to be a space after this because it needs to be precisely and specifically match that. Nothing, not even close. It has to get precisely exactly the same value. So it should work now. Yes, education top 20. Certain things, especially variable names, object names, they have to be like super specific. And newer students, I feel you, sometimes you're like, oh, is it that specific? Yes, it's that specific sometimes. Kiribati, Tuvalu, Bolivia, they have very high education spending. Good for them. I just don't know why. Maybe they emphasize education a lot. Maybe their GDP is low, that spending on education covers so much of their national GDP. They may have decided to increase education spending very aggressively. I have no idea, but good for them. I'm going to visualize this very quickly. I can just cheat and copy the code that I already wrote above. Instead of military top 20, I can just change this to education top 20. Instead of a more aggressive militaristic color, I can get a calmer, soothing color, maybe. Yeah. Part of it, top education spenders country, the minimal. Yeah. So let's plot. Nice. Good. Good. Now, what I can do is I can do the same thing for healthcare spending because we also downloaded healthcare data from World Development Indicators, top 20 countries by healthcare spending 2023. This is not 2 anymore. This is 3 because we downloaded 2023. we have to plot this. I'm copying everything from above. So this is not education top 20. This is health top 20. And in filter indicators, close this, close this, close this, close this. World development indicators. This is health GDP. Copy this. I'm going a little bit fast by now because one, I think you're more comfortable, and two, you can always pause and continue. So instead of education GDP, I can do health GDP year 2023. So I'm going to do ggplot. It's not education anymore. It's health. Reorder for health. Let's get this time. Let's get green, like a brighter green. Okay. Value top health spenders. Theme minimal. Coop. Yes. Oh, I closed it. Top health spenders: Germany, Canada, Sweden, Austria, United Kingdom. So it's actually a proxy for maybe a high level of development with some outliers, but it generally looks like, a list of very developed countries, to be honest with you. Nice. Um, Maybe what we can do is that we can do a little bit more advanced, um, not advanced, but more interactive plotting. So for interactive plotting, we go all the way back and download and install a package by now, just like copy and paste. So the package that we're going to download is Plotly, interactive plotter of ggplot. Yes. And library Plotly. Okay. So okay, so let's look at top 20 in all indicators: military, healthcare, education, top 20 of all world development indicators, pipe, group by indicator, filter by year, um, maximum value, whichever year is the top year available value. If it's 2023, it's going to get that. If it's 2024, it's going to get that. So it has to be maxed year, arrange by descending value, slice head. By now, look, I'm not like typing everything anymore. I'm using the benefits of using an IDE, an integrated development environment. Our studio is giving me hints. I can copy paste. I can select. So it's not like typing all the time. At some point, you start using these like quick enablers, which is going to help you quite a lot. N equals 20, but I'm still making mistakes because this is the first time I'm typing on this keyboard, and I'm having a lot of difficulty. I'm going to ungroup the subgroupings, the select, indicator, and country. So top 20 of all. So education, Namibia, Lesotho, Kuwait, health, Germany, military. So for all indicators, it is going to give me top 20 of all. So we have to also do WTI, the total of all these indicators. WDI, pipe, semi-join. Oh, I haven't taught you how to do join. So, okay. Left join, right join, inner join, semi-join, SQL join. So it's basically coming from um, SQL language. You're basically merging two data sets one another. Inner join basically combines them. Left join, you join the smaller part of a second table, join into the first table. Right join, the same way, full. The best way to look at this is, uh, no, this is, I think, a nice explanation. So you are basically creating expanded data sets or newer data sets by combining two different data sets. The principle of inner join is you select and combine two common parts of two different tables. A left join takes primarily the first table as the joining principle. Right join takes the second table as a joining principle. Outer join, full outer join means that two tables are combined fully. But on the other hand, semi-join is, let's see if it brings in properly. Semi-join, anti-join, and natural join. These like column separation and column joining principles. It practically gets two inner parts of a database and then joins them. It is going to be clear, hopefully, once I explain what I'm trying to do. So I'm going to semi-join top 20 of all by indicator and country. And then arrange them by indicator, country, year. Because now I'm going to visualize them. Yes. So it's like all of the education values of the top education spenders, all of the healthcare spending values of top healthcare spenders, all of the military spending values of top military spenders joined using the semi-join function. And now we are going to create a visualization out of this. Um, I'm going to write a long code, so it is always good to, um, let's say, WDI top 20 plot. This is going to be my object. It is going to take GG plot because it's going to be a long code. I have just started to spread my uh, parentheses from here on out. World development indicators. Let's take top 20 of those. I'm going line by line. It's going to take longer vertically, but it's going to be clearer, hopefully, what each section does. X is going to be year. Y is going to be the value. Each part is going to be colored by country. Grouping is going to be based on country as well. Each country is going to be colored and grouped separately. Then I want a pop-up to appear in each value that my mouse. I'm trying to create a um, interactive visualization now. So it's going to create a pop-up, which is going to give me a text, which is going to paste 0, which is concatenate the strings, in which it is going to say indicator, and it is going to take the values from my indicator section. Now I'm adding JavaScript notation. So the R code, which is going to get country. You're going to notice what these do when the interactive visualization finally appears. Again, JavaScript, BR, year, be careful with, so indicator, it's going to show something like which indicator, and it's going to take the values from the indicator data that I have, which country it is going to get from the country list that I have, and it's going to display it here. So be careful with the spaces and the orderings in this case. Value, no, sorry, it has to be BR. Value, it is going to, it's going to show two values to me, round, value 2, and it's going to, after giving me the percentage value, the text has to continue by saying percentage of GDP. Here, I have to now add geom line. Geom line. Yes, because it's going to be a line graph that I'm going to be doing. Geom line width, how thick the line is supposed to be. Let's do 1. If you don't like it, you can change it. Facet wrap. Facet wrap is an important function. I never talked to you about it, but facet wrap, I'm going to map 3 different line graphs. Facet wrap allows me to separate these line graphs and show them in one single interactive graph. It basically separates plots by indicator. And for this, I need the tilde sign. I don't have it on my keyboard. I have no idea where it is. And so I am going to cheat and copy it from the internet. Facet wrap is going to be indicators. Sorry, indicator. Scales, free y. So the y-axis has no upper limit, no lower limit. It's basically a free y scale. If you try one without the scales option or the free y option, see what it does. Free y basically prevents the values from squeezing into one another too much. Labels, title is going to be top 20 countries by spending, military, health, education, comma. You can say it's subtitle if you want. You can add subtitle. say percentage of GDP, comma, X is going to be year, but it has to be wrapped as such. Y is going to be percentage of GDP values, and color has to be country. Yes, the code continues. Theme, minimal. Base fonts, so you can also change the total fonts in the theme that you are choosing. 12 font is always, a good place to start. If you don't want it, you can change it. And theme is the plot title. Let's make it bold. Element, text, space, bold, comma, strip, text, element, text, space, once again, bold, sorry, bold, size 12, and we need a legend to show what these things are. Legend position, I mean, keep things readable, maybe like a hovering, no position. Let me just modify as I see fit and what. Okay, gradually we are building bigger and bigger and bigger code structures. So beginning from here all the way to here, this is one line of code. I hope I haven't made a mistake. I'm very hungry, guys. I haven't eaten anything since I started these lectures. It's been like 6 hours or something now. So run. No, use of light error mapping not created by an AES. Okay, I did create an aesthetic. Did I forget the AES? ggplot, drop false, by abort. Oh, so the error is because it's not always a good idea to write such long codes. The ggplots, this part code, the parentheses had to be closed. Notice where ggplot parentheses opens and closes. The geom line, this part, should not be part of the initial part of the code. So these two parts of the code, separated by this plus sign, this part needs to be closed off before we start the geom line part. So now, hopefully, it has to work. So now we have this not as a data frame, but as a graphic option. Now, what I'm going to do right now that I have this clearly identified as a plotting code, I need to plot this. Let's convert this into an interactive. This is going to use ggplotly object. It is interactive JavaScript object. It is going to plot WDI top 20 plot with tooltip C text so that the tooltips appear as text. Let's give this a little bit of space. Let's run this. Yay. Okay, let's not export this. Let's zoom into this. Let's make it big. Now, facet wrap basically takes these three different indicators and put them into a separate graph. And the reason why we made this into an interactive is that, as you can see, when you hover on every single indicator, it is going to give you what indicator it is, which country it is, what year is it, value, what percent of GDP. Remember, we wrote all of these things very clearly. So this is, I think, a nice visualization. Can we zoom? No. If you want, you can facet them more horizontally, not like vertically like this, if you like. But generally, this is largely how you build a visualization. I don't have much left. I would rather finish this. You know, I think maybe let's visualize more, maybe top 20 countries of all, which would take GDP top 20. This GDP top 20 comes all the way back from our first session. So I'm right now combining objects created from data sets we imported as CSV and as API, so that you have some also practice with combining data sets extracted from different parts. This is all the way back from line 53. This is this GDP top three, the CSV file GDP figures. So I'm taking this. I am doing distinct. Each country that is a country name. Back tick. Let's copy the back tick. From here, each distinct country name. Pull. Okay. Top 20 countries. Okay, it's here as value, not as a data frame. Now let's build a correlation matrix, which is interactive. Build country correlations function. This is going to create world development indicators, data frame, indicator, label, keep countries. Now, what I'm going to do after this, I have to put it here. I need to use a curly bracket because now I'm going to write a function. Notice this is a simple parenthesis. This is the curly bracket. In between the curly brackets, I am going to hit enter so that the whole function starts and continues from there. And here, what I'm doing is wide world development indicator data frame. It's going to be created here. Filter by indicator that has to match strictly to the indicator label. Country in keep countries, then select country, year, value. This is basically building an interactive visualization, but first we have to, clear and parse the data. Each distinct is going to pivot wider because we now have to we did longer because we had to do longitudinal time series analysis. Now we're putting it back to wider because we have to do correlation matrix, correlation analysis. Names from country, what you are correlating, their names are going to come from country. Values are going to come from the value column that we have, and then arrange by year. This is not over, so we are continuing. This is going to be one big, large function. Mat is the mathematical equation in which wide is going to select but drop the year. And then mat is also going to take in, this is still within the function, mutate all mat as numeric. And we are dropping all not available values if they still exist. But we are using an edged bracket. The rows are not going to get any treatment. The columns are going to get call sums is na mat. They have to be greater than 1. If else, drop false. And then if number of columns in mat are smaller than 2, another function, a function within a function, stop correlating and paste not enough data. So we're learning a little bit of like computer programming as well, not just data science. And then identify the indicator label. So which one actually doesn't have proper data. Now, this first function, so the inner function finishes here, so enter, but the bigger function continues. So here we basically correlate our mat, the data that we're going to be using. The correlation has to be pairwise complete observations, and the method is going to be Pearson. Fine. We are going to be running this whole thing, assuming that I'm very tired and hungry. I'm giving 90% chance that there's going to be a mistake here. No, there's no mistake. Good. Nice. Okay. Writing a long code and discovering that you don't, you haven't actually made a mistake is really, really interesting. So now we compute correlation matrices for each indicator. So correlation for military is going to come from build country correlations, the entire code we wrote above. It's going to take world development indicators, military percentage GDP. It's giving me this ending of the quotation always in the wrong place. Top 20 countries, close parentheses. So this is going to create country by country comparisons of military spending indicators, core military, but it is still a date. It's okay. Nice. So this is what it has created. It took all the military spending values of all countries and it basically correlated with, it's like a gigantic pairwise correlation table. So Australia's military spending correlation with other countries, basically the ones that don't have missing values. Since 1960, only a small number of countries have uninterrupted data because for us to be able to properly correlate, we need to have as much data as possible. Only a handful of countries actually fulfill this criteria. So that's what we are going to be working on. No, actually, these are top 20 countries. Sorry. This is the military correlation matrix or of the top military spenders. Sorry, my bad. So we can copy this and we can do exactly the same thing for education. Build country correlations, the VDI. It is education GDP, still from the top 20 countries. We run this as well. Correlation education. How countries' education spendings, top spenders, that was not available here. Two available. Three, four. Oh my God. And we can do the same thing for essentially healthcare. Build country correlations. This is health GDP of top 20 countries. Core healthcare. Yeah. So what we're doing right now is that in the first part of the exercise, we downloaded a CSV that contains that contains all of the GDPs for all years, for all countries. We cleaned that data and formatted such that we extracted the top 20 GDP countries, richest countries in the world, essentially. And Turkey is in that list, 16th, I think. And right now, we are using the objects that we created from our first exercise and merging it with objects that we created in the second exercise. We are merging CSV data with API data. It's very critical. It's one of the most important skills in data science. So now we are going to be doing an interactive visualization of these correlations. This is going to start with Plotly. It is going to plot or heat map because I want to create a heat map. I need to create a function, formats, title, text. And here I'm beginning the function. Right in the middle, I hit enter so that I can type things more clearly. So plotly, initiate a plotly visualization, like ggplot, but interactive. It is going to take its x. Oh, sorry. Oh, no. No. Where's my equal sign? Okay. X from column names, formats. Y is going to take its row names from formats. Z is format. You're going to understand what this format is just now. Type is going to be a heat map of correlations. Colors, uh, color ramp, color interpolation. It is going to contain two color values, a maximum value and a minimum value. Let, for example, let that, sorry, let that be red. No. But no. Color map, color ramp. This has to be red, let's say. White. Very interesting. Why is it giving? Okay, gave me red. Has to be lowercase. And blue. Okay. Uh, Z minimum. So the correlation of the heat map is the minimum is 1, -1. It's a Pearson correlation. Z max is 1. Text is going to be round from format to over templates. Pastes. Oh, I forgot to add comma. That's why expected comma after expression. Each line has to be connected to the rest. So that's why it's giving me an error. A row is going to be the y axis, and it's going to display a text with the br function. Column is going to be, it's coming from the x-axis, and it is going to display a text of this as well. Then the R here is the Pearson correlation R, the coefficient that we're trying to do. And it is going to be, this is slightly more complicated, equals F, close the bracket, and then type bruh, and then close the bruh. At this point, this is no longer just our language, this is our language combined with JavaScript, HTML, that kind of stuff. At any given time, I mean, I've made a mistake. If we make a mistake, we correct this. Run. Oh, okay. No mistake. Interesting. Good. So now, interactive visualizer. So plot military is going to be plot correlation heat map of core military correlations of military spending levels. Correlation military, and it's going to say correlation military spending of top 20 countries. Let's see if I made a mistake. No mistake. Good. P military is here. We can also do the same thing, copy and paste this, interactive visualizations for other indicators as well. This has to be plots of education. It is not going to be core military, of course. This is core education, the object we created before, correlation, education, spending of top 20 countries. Sorry, education. Sorry. Okay. And health. Plot of health care. Plot here, not core military. This is core health care. The data frame that we created earlier. Okay, spanning of top 20 countries. Okay. Joop. Now, everything is ready. Drum roll. From here, if I say just P military, because I have added every single data cleaning, data formatting, adding the visualization basics, parameters, text, labels, axis, everything. Just the thing to visualize this right now is just running this code P military. And this is a correlation matrix. This gives you interactive, as you see. Oh, there's something wrong. You see, like it says R 0.48 extra extra. I made a mistake by not closing that paragraph properly, and it is this one. That is why it says extra extra. So I have to first go back, run this again, run. Yes. And then run these again, run, and run this again. Yes. Zoom. Oh, there you are. Close this. Maybe I need to run this again. Okay. Yes. Now you can see a beautiful correlation matrix that shows countries by military spending, which countries' military spending indicators are very close to each other. For international relations people, this gives you an idea, especially if two countries are also geographically close by, it gives you whether those countries see each other as enemies or allies, because countries that spend on their military together are either in an alliance like NATO or ASEAN, or are fighting with each other. That's why their military spending is basically correlating with one another. So let's see where Turkey is most correlated with. Turkey is most correlated with Indonesia. Turkey and Indonesia are actually military um, industry partners. There's a lot of trade going on, so that would make sense. Um, Turkey, of course. Spain, Turkey, another ally of Turkey in the NATO, especially one of the closest partners for Turkey is Spain. But other than that, for example, let's look at Italy. Italy's spending is a lot correlated with Australia, with Canada, with France, with Germany, in Italy, because of the European Union dimension, probably. Because look, Switzerland spending is also heavily correlated. It makes a lot of sense. You can spend hours in this correlation matrix. It gives you quite a lot of new information about the top spenders. Same goes for education spending, which is not as correlated because it's very rare that countries look at another country and say, oh, yes, let's spend on education together. But for example, Brazil, United Kingdom, are very closely correlated. Turkey and Brazil are also very highly correlated. Mexico and Turkey. I don't know why this is the case. Maybe student diplomacy. I don't know, but this is not something that is highly correlated anyway. You're going to see that most of the time, for example, Poland, India, their education spending is very inverse. Probably, oh, there's some missing value here and here and here. No, it's just zero, completely unrelated. I think like an education expert would be able to interpret this better. I'm not really an education policy person, so I wouldn't know why this is happening. Finally, let's do health. Health is relatively more correlated. Um, Health tourism? I don't know. But there are countries like Turkey, for example, that is not really correlated with any other country. That's very interesting to me. And India. Uh, India and Turkey are very much outliers in this case. I don't know, like India has like really fantastic doctors. Turkey has a good public uh, healthcare system that works relatively okay. I wouldn't know why this is happening. So that's the beauty about correlations and correlation matrices. Even though we don't know a causal relationship yet, because I'm not the expert, it gives you patterns that really get you thinking. But while doing those, congratulations, you wrote 334 lines of code, especially given this is still an introductory course. I think it is very, very interesting. So basically, what have we learned? You imported and cleaned real world data, right? It's not a pre-cleaned data. It is not like training data. I don't like working with training data. Just want my students to like go into the world, get raw data, and try to find their way across that raw data. You learned how to handle missing values uh, that appear in non-standard forms like this dot dot format, how to systematically convert them into proper NA values in R. You explored the structure of your dataset using glimpse and summary. You distinguish between rows, columns, variable types, and missingness. You learned how to pivot longer and pivot wider. It's going to take a while to master this, but at least you use this in four different data sets. And it's important from spreadsheet to long, tidy formats. It gave you flexibility to reformat data for different analysis, like time series visualization, descriptive statistics, and correlation matrices. You learned how to calculate basic summary measures, mean, median, standard deviation, minimum and maximum, both globally and by country. You compared patterns of GDP, military, education, health spending across countries over time. You built nice visualizations using grammar of graphics approach in ggplot2. You created bar charts of top GDP, military, education, and health spenders, faceted line plots showing changes over time across multiple indicators. You created box plots and heat maps to visualize patterns and correlations. You learned how to use reorder, coordinate flip, facet wrap to make visualizations both readable and comparative. You connected directly to the World Bank database using the WDI package, allowing you to access the latest global economic and social indicators dynamically using an API. You practiced defining indicator codes, setting time ranges, and filtering out aggregates of incomplete data. You built correlation matrices using core function to understand how indicators move across countries and years. You visualize these relationships using GG correlation plots, static, and also plotly heat maps, JavaScript interactive. You learned how to interpret positive, negative, and weak correlations in the context of social and economic behavior. You use Plotly once again to make interactive graphs where hovering on it reveals country, year, and value information. This is useful in multi-country time series analysis dynamically, especially when comparing dozens of countries. In those contexts, static graphs are not very helpful. Dynamic maps are more helpful. By comparing GDP, military education, and health spending data, you learn to connect economic indicators to real-world governance and policy debates. You saw how rich and poor countries differ in resource allocation and how these spending patterns shift over time. I think the most important part of what you learned, you practiced a full data science pipeline. Data collection, data cleaning, data transformation, data visualization, data analysis, data interpretation. If you master this pipeline, you can master any aspect of data science along the way. You learn to move fluidly between static and interactive visualization tools. And basically, you use both CSV and API for a coherent workflow. Now, what you can do is you can save as my surname is Ünver. The course is IR 421, World Development Indicator CSV API exercise. Save this both here and save it again using here. And also save as, say the same thing to, for example, your desktop, because we did quite a lot and I want to make sure that you have done your homework. This is a relatively easy homework because you're watching a video essentially, but go here, WDI CSV API tutorial exercise uploads, and upload your R file here until Monday. The deadline is this. Because I'm the professor of this course, it doesn't give me an option to upload the R file, but you'll be uploading your R files here because I need to make sure that you are really doing the work. So it's been a pleasure. I think you benefit from this session somewhat. You can watch this as many times as you like. The good thing about YouTube is that you always have this repository of information right next to you. We covered quite a lot. I feel now you'll be more comfortable with my more advanced text mining, topic modeling, network analysis, network graph, spatial analysis, GIS, digital mapping, machine learning, neural networks classes in the coming weeks. It's been a pleasure, and I'll see you on Tuesday. Take care. Bye.